Over 2 billion years ago, Earth's skies and seas held almost no breathable oxygen. Then slowly and irreversibly, tiny microbes began to flood the planet with this reactive gas, triggering one of the most dramatic chemical revolutions in Earth's history. The Great Oxidation Event reshaped ocean's atmosphere and the destiny of life itself. If you enjoy calm journeys through deep time, please like, subscribe and share. And tell us in the comments, what part of Earth's early oxygen story are you most curious about? Thank you for watching. Now let's begin. In the early Archean, the planet turns beneath a sun that shines more weakly than it does in later ages, yet still delivers enough energy to keep liquid water present at the surface. The star in the sky is fainter by a significant fraction, so the total light that reaches the top of the atmosphere is lower, and the balance between incoming sunlight and outgoing heat must be held by a different mix of gases from the one that surrounds the modern world. The air is thick in nitrogen and rich in carbon dioxide and other greenhouse gases that trap heat, while free oxygen is essentially absent. In this time, the atmosphere is strongly reducing, meaning that many compounds in the air and at the surface hold their electrons tightly and prefer to react with any oxygen that might appear. Methane and other reduced gases released by volcanoes and by early microbial activity can build up to levels that make a strong contribution to warming, offsetting the weaker sun and helping to keep the surface above the freezing point of water over much of the globe. This mixture of gases makes the air dense with infrared absorbing molecules, so that heat leaving the surface is intercepted and re-radiated many times before it can escape to space. High above the surface there is little ozone because ozone depends on free oxygen in the air, and that free oxygen is vanishingly small. Without a substantial ozone layer, more high-energy ultraviolet radiation pours into the upper atmosphere and can reach the shallow surface waters of the oceans and exposed land. This radiation drives chemical reactions in the air and in thin surface films on rocks, and dust grains breaking molecules apart and allowing new combinations. Some products of these reactions are short-lived radicals that quickly pass their energy onto other species, while others are more stable molecules that accumulate over time and join the background chemistry of the Archean sky. The sky during this interval is likely hazier than the clear blue that becomes familiar in later times, because high levels of methane and photochemical smogs formed by sunlight acting on reduced gases can produce suspended particles. These particles scatter light and can give the air a muted quality when seen from the surface, though the exact colour and appearance are constrained only indirectly from geological and geochemical clues preserved in ancient rocks. The scattering behaviour of these aerosols influences how much sunlight reaches the lower atmosphere, and the surface redirecting some radiation back towards space and some downward. In regions where aerosols are abundant, the surface receives more diffuse light and less direct glare, while in clearer regions the sun appears sharper, and the contrast between day and night is stronger. Clouds form and dissipate above this unfamiliar atmosphere, controlled by the evaporation and condensation of water, just as they are in later eras, but moving within different temperature and humidity patterns. In some regions, the air column supports thick cloud decks that reflect a portion of the incoming sunlight back into space, while in other regions the sky remains more open and allows more radiation to reach the lower atmosphere and the surface. The height at which clouds form, the amount of water they hold, and the speed at which they move all respond to the vertical temperature structure of the Archean atmosphere, which is influenced by strong greenhouse warming near the surface and by radiative losses higher up. Storms develop as warm, moist air rises and cools, but the statistics of these storms, their frequency and intensity, unfold against the background of a greenhouse, warmed yet faintly lit planet. Thunderclouds can tower through much of the troposphere, releasing rain and transferring heat upward, while broader stratiform cloud sheets stretch over vast areas and soften the daily cycle of heating and cooling. Over long spans of time, the mean climate remains clement enough for liquid water to persist in extensive oceans and on flooded low-lying crust. But the details of temperature and rainfall patterns are set by continental positions, seafloor topography and atmospheric circulation that are only partly known from present evidence. Near the equator, stronger solar input encourages more vigorous convection and more frequent clouds, while at higher latitudes the balance between greenhouse warming and lower insolation determines whether ice can appear seasonally or remain rare. The pressure at the surface may be higher than in later ages if nitrogen levels are elevated, or it may be closer to later values if large amounts of nitrogen are already stored in rocks, and the deep interior and present data place only broad bounds on this aspect of the Archean air. What is clear from multiple lines of evidence is that the atmosphere holds far more carbon dioxide and other greenhouse gases than in later times, and almost no oxygen, and that this composition maintains a long-lived balance between the faint solar energy supply and the need to keep surface waters from freezing solid on a global scale. The upper boundary between atmosphere and space in this interval is also shaped by the behavior of the young sun. The star emits stronger winds of charged particles and more frequent high-energy flares than in its later quieter state. These winds interact with the upper atmosphere and with any magnetic field generated by the interior of the planet, stripping some gases from the outer layers while deflecting others and causing complex auroral displays near the magnetic poles. In the thin rarefied gas high above the main air column, atoms and molecules are ionized and follow magnetic field lines feeding a dynamic region where space weather and atmospheric chemistry meet. The rate of loss of gases to space under these conditions is still debated, and current models allow a range of possible histories, but they agree that the bulk atmosphere remains in place and continues to evolve through outgassing from volcanoes, weathering of rocks, and exchange with the oceans. Over geological timescales in the early Archean, this exchange between the surface and the air maintains an atmosphere that is thick, warm and poor in free oxygen. It sets the chemical and physical context that defines the outer layer of the Earth system at this stage in its history, fixing the conditions under which oceans form rocks alter and early microbial communities operate. In the early Archean, the ocean spread across most of the planetary surface, filling deep basins and drowning low-lying crust, under a continuous mantle of water that moderates climate and absorbs heat from the atmosphere. The water is slightly acidic because it holds dissolved carbon dioxide and other volcanic gases, and it is rich in dissolved metals such as iron that flow in from the young crust and from countless hydrothermal vents along the spreading ridges of the seafloor. Free oxygen is essentially absent, so iron and many other elements remain in reduced forms that stay dissolved or precipitate as minerals very different from those that dominate in later oxygen-rich times. The uppermost layer of the oceans interacts most directly with the atmosphere and with incoming sunlight. In this surface layer, wind and waves mix heat gases and particles, creating a zone where temperature and composition can change over relatively short distances. Below this mixed surface layer, water becomes more stable and stratified. Stratification is the tendency for water of different temperature or salinity to form distinct layers that do not mix easily. In the Archean, this stratification often separates a warmer, more variable surface from a deeper, cooler interior that remains dark, dense, and poor in oxidized species. Across entire ocean basins, slow circulation moves water masses along complex paths. At the surface, currents driven by wind and by the rotation of the planet carry warm water away from regions of stronger heating and bring cooler water back in, return forming broad gyres and flow patterns that depend on the positions of continents and ridges. In the depths, circulation is controlled more by density differences and by the slow rise of heated water from hydrothermal systems. Cold, slightly denser water may descend along some margins, while hot chemically rich fluids leak from the seafloor and rise until they cool and mix with surrounding waters. These hydrothermal systems are especially important in the Archean because heat flow from the interior is stronger than it is in later ages, and spreading centres and volcanic arcs are common. At countless vents and diffuse flow sites, seawater percolates into the crust, reacts with hot rocks, and returns to the ocean charged with metals, reduced sulfur, and other dissolved species. When this fluid meets the ambient seawater, minerals can precipitate and form dense plumes that drift away from the vent fields, gradually settling through the water column and altering the chemistry over wide areas. The balance between hydrothermal input weathering on land and burial of minerals on the seafloor controls the overall composition of the oceans through long spans of time. Temperature in these Archean oceans varies with latitude, depth, and time, but overall the water is kept in a liquid state by the combination of greenhouse warming and internal heat flow. Near the equatorial regions, surface waters can become relatively warm, promoting vigorous mixing and evaporation. Rising water vapor feeds cloud formation and rainfall, which in turn delivers dissolved ions back to the ocean from the weathering of rocks on whatever land masses exist above sea level. Toward higher latitudes, surface waters are cooler and seasonal or regional ice may appear in some intervals, but clear evidence for global glaciation in this earliest time is limited and constrained to specific episodes. The average salinity of the oceans is set by the long-term exchange of ions between seawater crust and mantle, and may differ from modern values, but whatever its exact level, salinity influences the density structure of the water column, and thus the strength of stratification and circulation. Light penetrates only a limited depth into these Archean seas, and the depth of penetration depends on the concentration of particles and dissolved substances that absorb and scatter radiation. In clearer regions, short wavelength light can reach tens of meters below the surface, while in regions rich in suspended particles, iron or organic matter light is absorbed more quickly, and the zone that receives enough energy to support photosynthesis is thinner. Below this photic zone, darkness prevails, and life that exists there must rely on chemical energy from the breakdown of organic matter, sinking from above or from reactions near hydrothermal systems and in the crust. The chemistry of the water column is tightly linked to the lack of free oxygen in the atmosphere. Dissolved oxygen is nearly absent except possibly in very local microenvironments, so the dominant forms of many elements are reduced. Iron commonly exists as dissolved ferrous iron in deeper waters, giving them a capacity to carry large loads of metal until conditions change and minerals precipitate. Sulfur is present mainly as reduced sulfur species such as hydrogen sulfide and various dissolved ions which can build up in deeper or restricted basins and participate in a rich suite of redox reactions with metals and organic matter. Carbon moves between inorganic forms such as dissolved carbon dioxide and bicarbonate and organic forms within microbial biomass and detritus, with the exact partitioning controlled by pH, temperature, pressure, and biological activity. Nutrients such as phosphorus and nitrogen circulate through the water column and between sediments and overlying waters, supporting microbial communities that occupy surfaces, interfaces, and particles. On the scale of whole basins, the Archean oceans are not uniform. Some regions are closer to volcanic arcs or spreading centres and receive more hydrothermal input, while others lie down current of weathering continents and receive more river-borne solutes. Shallow shelves and platforms where they exist allow interactions between seawater sediments and light that differ from those in the open ocean, and enclosed basins can develop distinct chemical signatures if exchange with the wider ocean is limited. Over time, these differences create a patchwork of oceanic conditions with gradients in temperature, salinity, redox state, and nutrient levels. Circulation acts to smear out some of these gradients while preserving others, and the overall picture is one of a dynamic but systematically low oxygen world ocean that sets the stage for the interactions between water rock and life that follow in later stages of Earth history. Within this environment, currents' upwelling zones and density fronts create boundaries that concentrate particles and organisms, while vast interior regions of the basins remain more homogeneous. The oceans of the early Archean thus form a complex layered system in which physical circulation and chemical composition are closely intertwined. This system exchanges matter and energy constantly with the atmosphere above and the crust below, and it provides the medium in which early microbial ecosystems develop, diversify and respond to changes in the balance of gases and elements at the planetary surface. In the early Archean, the solid outer shell of the planet is thinner and hotter than in later times, and heat from the interior moves upward more vigorously through this shell. The crust consists of a mixture of dense oceanic plates and small buoyant fragments that begin to resemble the seeds of continents. Yet these fragments are smaller and more unstable than the broad continental masses that appear much later. Volcanic arcs and plateau-like regions dot the surface where plates sink back into the mantle, or where hot plumes rise and long chains of volcanoes release gases and ash into the atmosphere, while fresh lava spreads over the seafloor and emerging land. This restless surface sets the boundary conditions for the waters and the air above, and it also provides the mineral surfaces on which chemical reactions proceed and on which early sediments accumulate. The rocks that make up the Archean crust are rich in iron and magnesium and often form a distinctive family of lavas and intrusive bodies. Some lava flows are extremely hot and fluid compared with most modern examples, reflecting the higher internal temperatures of the planet and the ease with which mantle material melts. When these rocks are exposed at the surface, they interact with the atmosphere and with rainwater and seawater in a set of processes known as weathering. Weathering is the gradual breakdown and chemical alteration of rocks at the surface under the influence of water gases and biological activity. In the Archean, weathering proceeds under an atmosphere that lacks free oxygen. So many reactions that dominate in later times, such as the formation of thick layers of reddish iron oxides in soils, are limited or absent. Instead, reduced minerals dissolve or transform in ways that keep iron and other elements in forms that can be carried by water into rivers, coastal zones, and the open ocean. On exposed land, rainwater that absorbs carbon dioxide from the air becomes slightly acidic and flows over and through the rocks, removing some ions and leaving behind residues that form the earliest recognizable soils. These primitive soils can be thin and patchy, especially on steep or volcanically active terrain, yet they already record the balance between atmospheric gases, water, and the crust. Where the land is low and relatively stable, layers of soil can build slowly as fresh material continues to arrive from dust and ash, and as minerals change their structure in response to contact with water. In these soils, the lack of strong iron oxidation features and certain mineral assemblages indicates that the air above them remains poor in free oxygen and rich in reduced species. Along coastlines and in shallow seas, the products of weathering, along with volcanic ash and particles, eroded from rocks by flowing water, settle to the bottom and begin to form sediments. Over time, these sediments are buried by additional layers and compacted into sedimentary rocks such as sandstones, shales, and chemical precipitates. In some Archean basins, layers of fine-grained material alternate with coarser deposits in rhythms controlled by tide storms or longer climate cycles. Chemical sediments form directly from seawater, including carbonate-rich layers and iron-rich horizons, store information about the composition of the oceans and atmosphere at the time they form. In a world without significant free oxygen, iron-bearing minerals can precipitate as reduced compounds or as mixtures of different iron phases, and these assemblages differ from those that dominate in later, more oxidizing periods. The interplay of hydrothermal input from the seafloor and weathering input from land produces basins where iron, silica, and other dissolved species can reach concentrations high enough that small changes in temperature mixing or local redox state cause minerals to fall out of solution. The resulting bands and layers capture subtle variations in the chemistry of the water column and in the balance of reduced and oxidized species, even when overall conditions remain strongly reducing. On the floors of deeper basins, far from land and away from strong currents, very fine particles of clay and organic matter drift down from the surface ocean and settle through the dark water. Over long periods, these particles build up thick packages of mud that gradually transform into shale. Organic matter within these sediments comes from microbial life in the surface waters and from communities that live attached to particles or at interfaces within the water column. As burial proceeds, this organic material is compacted and heated, and some of it is broken down or altered, while some remains locked within the rock. The amount and type of organic carbon preserved in these sediments offer a record of biological productivity and environmental conditions, and in the Archean they point to active microbial ecosystems operating in oceans and possibly on land, even though fossils of individual cells or communities are rare. In some shallow water settings, hard mineral surfaces such as carbonate platforms, volcanic rocks, or early sandbars provide places where microbial mats can grow and trap particles. These mats are layered communities of microbes embedded in sticky substances that they produce, and over time they can create finely laminated structures that are preserved as distinctive sedimentary features. The growth and decay of these mats influence local chemistry by taking up carbon dioxide, releasing metabolic byproducts, and changing the acidity and redox state near the sediment surface. In an atmosphere that lacks free oxygen, many of the reactions within these mats and in the underlying sediments involve reduced iron, sulfur, and nitrogen species, and the balance among these reactions leaves an imprint in the minerals and isotopes that form. The tectonic setting of a sedimentary basin also matters. In areas where the crust stretches and thins long-lived, subsiding regions can develop, allowing thick sequences of Archean sediments to accumulate over tens of millions of years. In contrast, in more active regions near volcanic arcs or collision zones, sediments may be rapidly buried, heated, and deformed, so that original textures and minerals are partially or completely overprinted by later metamorphism. Even when metamorphism is intense traces of the original environment, can sometimes be read in mineral assemblages and in the isotopic composition of certain elements, providing a window into the conditions at the time of deposition. Through all of these processes, the early Archean crust with its interplay of volcanism, uplift, erosion, weathering and sedimentation act as both a participant in and a recorder of the state of the surface environment. Gases released from magmas feed the atmosphere elements, leach from rocks, feed the oceans, and solids produced in the water or delivered from the air build new layers of rock. Over time, some of these rocks are carried downward into the deep interior, recycling their constituents, while others are uplifted and exposed again, completing cycles of interaction between the solid earth, the hydrosphere, and the atmosphere. In this way, the crust and its sediments hold a long-term memory of a world that is warm, dynamic, and strongly reducing, in which free oxygen exists only in negligible amounts, and in which the continuous exchange of matter and energy between rocks, water, and air maintains the prevailing low oxygen conditions at the surface. As time passes within the Archean world, the atmosphere that surrounds the planet remains dominated by nitrogen, carbon dioxide, and other reduced gases, yet tiny amounts of free oxygen begin to appear and then vanish in a continuous delicate balance. High in the air, some oxygen forms when ultraviolet radiation from the young sun splits molecules such as water vapor, freeing hydrogen atoms that can escape more easily to space and leaving behind oxygen that briefly joins the surrounding gases. This photochemical pathway produces only very small amounts of oxygen and does not build a lasting reservoir because the new oxygen quickly reacts with reduced species in the air or at the surface. Volcanic eruptions continue to release large quantities of gases like hydrogen, sulfide carbon monoxide and methane, each of which consumes oxygen when it reacts, and the overall atmosphere remains strongly reducing. Against this background, a more persistent source of oxygen begins to develop in the illuminated surface waters of the oceans. In these shallow sunlit zones, microbial communities that carry out a specific form of photosynthesis use light to split water and fix carbon dioxide into organic matter, releasing molecular oxygen as a byproduct. Photosynthesis in this sense is the process that uses light energy to build energy, rich molecules, and in its oxygen-producing form, it draws electrons from water rather than from reduced compounds such as hydrogen or hydrogen sulfide. The earliest steps toward this kind of metabolism may appear in stages with ancestral microbes using different electron donors before the fully water-using pathway emerges. By the interval in question, however, there is evidence that oxygen-producing photosynthesis operates in at least some microbial lineages and contributes a steady flux of oxygen to the surrounding environment. In the surface ocean, where these microbes form layered communities on sediments, volcanic rocks, and carbonate platforms, the oxygen they release does not simply accumulate in the air. Instead, it reacts almost immediately with reduced species dissolved in the water. One of the main sinks for this oxygen is ferrous iron, the reduced form of iron that is abundant in Archean seawater. When ferrous iron encounters oxygen, it oxidizes to ferric iron and can precipitate as iron-bearing minerals that settle to the seafloor. In this way, the oceans act as a vast chemical sponge that removes oxygen as quickly as it is produced, forming mineral deposits that incorporate the history of these reactions. Sulfur species also participate in these redox cycles. Reduced sulfur in the form of hydrogen sulfide or various dissolved ions reacts with oxygen to form sulfate and solid minerals, further limiting the amount of free oxygen that can diffuse upward into the air. The rate at which these sinks consume oxygen depends on the concentration of reduced species delivered from hydrothermal vents, volcanic activity, and weathering of rocks, and on the rate of photosynthetic production in the surface waters. As long as the supply of reduced species remains large compared with the biological oxygen flux, free oxygen in both water and air stays at extremely low levels. Rocks and sediments of this time preserve several lines of evidence for this delicate balance between production and consumption. Certain sedimentary minerals that contain iron, sulfur, and other redox-sensitive elements retain chemical and isotopic signatures that indicate strongly reducing conditions, even though oxygen-producing photosynthesis is already active. Detrital grains of minerals such as pyrite and uraninite, which are unstable in the presence of significant free oxygen, can survive erosion river transport and deposition in fluvial and deltaic settings, showing that oxygen levels in the atmosphere and surface waters are still too low to oxidize these minerals completely. At the same time, subtle changes begin to appear in some sequences of chemical sediments, hinting that local or transient oxygen, rich microenvironments may exist where oxygen sources are momentarily stronger than sinks. In shallow marine platforms, for example, layers of carbonate and iron-rich material may include intervals where iron minerals show partial oxidation, while adjacent layers remain dominated by reduced phases. These patterns can result from small shifts in the balance between photosynthetic production in the surface ocean and the input of reduced elements from below, as well as from changes in water column stratification and mixing. Over long periods, repeated formation and burial of such layers slowly draw down the global inventory of reduced species, preparing the system for later more dramatic shifts. Within this framework, microbial life continues to adapt and diversify. Communities of oxygen-producing microbes, often grouped under the broad label of cyanobacteria, in the rock record occupy niches where light is available, and the supply of nutrients allows sustained growth. They form extensive mats on tidal flats, shallow shelves and around emerging land masses, building layered structures that trap sediment and create microenvironments with strong gradients in oxygen sulfide and other chemicals over distances of only millimeters. Below the upper oxygen-producing layers, other microbes exploit the organic matter and oxidize compounds produced above using metabolisms that rely on nitrate sulfate ion or carbon compounds as electron acceptors. Deeper still, in anoxic sediments and waters, strictly anaerobic microbes thrive using reduced sulfur ion methane and hydrogen to sustain their energy needs. The presence of oxygen in the uppermost layers poses both a challenge and an opportunity for these organisms. Some lineages evolve mechanisms to tolerate brief exposure to oxygen, while others specialize in remaining within low oxygen or oxygen-free zones. The net result is a vertically structured ecosystem in which oxygen concentrations can vary from near zero in deeper water and sediments to small but measurable values just above active mats and in the thinnest films of surface water. Microenvironments where oxygen briefly accumulates are especially important in this stage. Overgrowing microbial mats during periods of strong sunlight and low physical disturbance, the rate of photosynthesis can exceed the capacity of local sinks to consume oxygen for short intervals. In these conditions, oxygen levels in a thin layer immediately above the mat can rise to values high enough to influence mineral formation and microbial metabolism. When the sun lowers, when currents or waves disturb the surface, or when metabolic demand from the community and from chemical reactions catches up, oxygen levels drop again. Similar transient oxygen oases can form in microlayers around individual filaments, grains or bubbles where photosynthetic activity is concentrated. These small zones do not yet contribute much to the bulk composition of the atmosphere, but they represent early examples of oxygen-rich niches that later expand as sinks weaken. Over millions of years in this late Archean interval, the interplay of oxygen sources and sinks slowly shifts global inventories. Weathering of crustal rocks on land gradually changes as trace amounts of oxygen in surface waters and soils influence mineral stability, even if the air above them remains effectively anoxic. Some reduced minerals become slightly less stable in certain settings, while others continue to persist, and the overall effect is a subtle alteration of the supply of reduced species to the oceans and the atmosphere. Meanwhile, continued burial of oxidized forms of iron and sulfur in sediments removes reducing power from the active surface system, locking it into the crust and making it unavailable to consume oxygen in the future. Through this slow progression, the planet enters a stage in which the first sustained leaks of biologically produced oxygen meet a still overwhelming capacity for chemical consumption, and the net result is a world that remains low in free oxygen, but that carries within its rocks, waters, and microbial ecosystems the marks of a growing imbalance that has not yet reached a tipping point. In a later stage of the Archean, the uppermost layers of the oceans become the main arena, where the slow rise of biologically produced oxygen encounters the chemical capacity of the surface Earth to consume it. The atmosphere above the seas remains effectively without free oxygen on a global scale, still dominated by nitrogen, carbon dioxide, methane, and other reduced gases. Yet the sunlit surface waters have changed compared with earlier times. In these mixed layers where light wind and waves continually stir the upper tens of meters, photosynthetic microbes are more widespread and more productive than before, steadily turning carbon dioxide and water into organic matter and molecular oxygen. The result is a persistent, though still modest, upward flux of oxygen into the surface ocean that interacts with a complex set of chemical sinks. The physical structure of the water column shapes how this oxygen is distributed. Warmer, less dense water at the surface overlies cooler, denser water at depth, forming a stratified column that resists mixing. In many regions, this stratification creates a sharp transition between a relatively well-mixed surface layer that exchanges gases with the atmosphere and a deep interior that remains dark and strongly reducing. Within the surface layer, winds and surface currents spread both oxygen and reduce species horizontally, so that patches of water with higher oxygen content can drift into regions where reduced compounds are still abundant. At the base of the surface layer, where it meets deeper, more reducing waters, a chemical boundary develops. Across this boundary, often called a redox front, chemical species change their oxidation state as they move upward or downward. Reduced compounds coming up from below encounter oxidants formed above, and both are transformed. In this pre-event interval, the dominant reduced species in the upper ocean continues to be ferrous iron, delivered from hydrothermal vents weathering on land and reactions in deeper waters. When ferrous iron meets oxygen, it oxidizes to ferric iron and can precipitate as iron-rich minerals that settle downward. The details of this process depend on pH temperature and the presence of other ions, but the overall effect is a continual removal of both iron and oxygen from the surface layer and their transfer to the sediments. Over wide areas of the shallow seas, this interaction produces horizons of iron-rich deposits that alternate with layers of silica-rich or carbonate-rich material. In some basins, these alternations show repeating patterns on scales of centimeters to meters, reflecting shifts in the balance between iron supply oxygen production and physical mixing. Manganese also plays an important role in this stage. Reduced manganese ions in the water can be oxidized by even small amounts of oxygen to form manganese oxides, which are efficient scavengers of other trace metals and can themselves be transported and buried. The onset of more frequent manganese oxidation in surface waters indicates that oxygen concentrations there, while still low in absolute terms, sometimes reach thresholds that allow these reactions to proceed. When such oxides settle into deeper, more reducing parts of the water column, or into sediments, they can be reduced again, releasing manganese and associated elements back into solution. This redox cycling creates a dynamic exchange between different layers of the ocean and between the water and the sediments, with oxygen acting as one of the key drivers. Sulfur species add further complexity. Hydrogen sulfide produced in anoxic deeper waters and sediments diffuses upward and can encounter oxygen at or just below the base of the surface layer. Where this interaction occurs, hydrogen sulfide is oxidized to sulfate and solid sulfur, bearing minerals consuming oxygen and shaping the vertical profile of both elements. In some restricted basins with high rates of organic matter degradation and limited mixing, hydrogen sulfide may approach the surface, squeezing the oxic zone into a thin veneer overlying sulfidic waters. In more open settings, the balance between oxygen production and sulfide supply keeps the interface deeper. The exact structure of these profiles is controlled by local productivity circulation and the geometry of basins, so the oceans at this time display a wide variety of vertical redox arrangements. The carbon system in the surface ocean also responds to the ongoing interplay between oxygen production, organic matter formation, and burial. As photosynthetic microbes fix carbon dioxide into organic carbon, they alter the relative proportions of dissolved inorganic carbon species and influence pH. Some of the organic matter sinks out of the surface layer, carrying reduced carbon into deeper waters and sediments, where it can be respired or buried. When organic matter is respired with oxygen, as the electron acceptor oxygen is consumed and carbon dioxide is regenerated. When respiration uses other oxidants such as sulfate or ferric iron, different reduced products form, including hydrogen sulfide or ferrous iron, which can later react with any available oxygen. Burial of a fraction of the organic matter without complete oxidation sequesters reduced carbon in sediments and removes it from short-term cycles, gradually changing the global balance between oxidized and reduced carbon. This process is one of the ways in which biologically produced oxygen can in principle accumulate, because for every unit of organic carbon buried, an equivalent amount of oxygen is not consumed. In this pre-event phase, however, the capacity of the surface system to consume oxygen through reactions with iron, sulfur, and other reduced components remains large, so only very small net oxygen surpluses persist. Nitrogen and phosphorus, essential nutrients for microbial growth cycle, through the surface ocean in ways that are increasingly influenced by oxygen levels, even when those levels are still low. Phosphorus is supplied by weathering of rocks on land and by recycling from sediments, and is removed by burial in organic matter and in minerals. The efficiency of phosphorus retention or release in sediments can depend on redox state, because iron oxides that trap phosphorus under one set of conditions can dissolve under another. Nitrogen moves through forms such as ammonium nitrate and dissolved nitrogen gas, and its transformations are tightly coupled to both oxygen and organic matter. In oxygenated microenvironments in the surface layer, ammonium can be oxidized to nitrate, a process that consumes oxygen, but creates a form of nitrogen that some microbes can use. Deeper down, where oxygen is absent but nitrate is available, other microbes can reduce nitrate back to nitrogen gas, completing a cycle that links surface oxygen dynamics to deeper processes. The combined operation of these nutrient cycles sets the productivity of the surface ocean, and thus the rate at which oxygen is generated by photosynthesis. Geological records from this interval preserve several indicators of the changing surface ocean chemistry. Iron-rich sedimentary sequences show patterns in mineralogy and layering that differ from earlier deposits, pointing to more extensive or more frequent oxidation of iron in shallow waters. Sulfur-bearing minerals and the isotopic composition of sulfur in sediments retain signatures of atmospheric and oceanic chemistry that require very low but perhaps fluctuating oxygen levels, with some changes suggesting that the atmosphere above the oceans is beginning to experience different photochemical regimes compared with earlier Archean times. Carbon isotopes in carbonate and organic phases reveal shifts in the balance between primary production, remineralization, and burial of organic matter, implying that the efficiency with which organic carbon is sequestered in sediments is not constant through time. Together, these lines of evidence indicate that the surface oceans in this stage are not simply anoxic extensions of the deep, but rather host-Patchian dynamic zones where oxygen and other oxidants appear are consumed and sometimes drive new mineral formation. At the scale of individual basins or shelves, the pre-event surface ocean can be pictured as a chemically structured environment, with a thin variable layer of oxygen, influenced water, overlying a much thicker reservoir of reduced water. Current storms and seasonal changes in mixing can cause the depth and thickness of this layer to vary, bringing oxygen into contact with fresh supplies of reduced species at some times and retreating at others. Over longer intervals, the continued production of oxygen by microbes and the gradual burial of oxidized forms of iron, sulfur, and carbon in sediments slowly lower the total capacity of the surface Earth to consume oxygen. Even so, the overall state of the system at this stage is still one in which oxygen remains a trace constituent of the air and water, present in localized and transient enrichments, rather than as a stable global background gas. The chemistry of the pre-event surface oceans thus reflects a world that is beginning to depart from its earlier strongly reducing state, yet has not yet undergone the large-scale reorganization that will later mark a truly different atmospheric and oceanic regime. In the late Archean stage that follows the first persistent leaks of biologically produced oxygen, The outer environment of the planet remains one of low global oxygen and strong greenhouse warming, yet the surfaces where rock water and light meet now support more extensive and more complex microbial communities than before. The atmosphere still holds only trace amounts of free oxygen far below the level needed to change its overall composition or to build a protective ozone layer, and it continues to be dominated by nitrogen, carbon dioxide, methane, and other reduced gases. Sunlight arrives at the top of this atmosphere from a sun that is still fainter than in later ages, but the combination of greenhouse gases and active oceans keeps the climate warm enough for liquid water to cover large areas of the crust. Against this backdrop, the key transformations that prepare the way for later oxygenation occur not in the air but in the thin skin of shallow waters and sediments, where microbes organize into layered communities and drive tightly coupled chemical cycles. In the oceans of this time, the most important habitats for these communities lie within the photic zone, the depth range where enough light penetrates to support photosynthesis, on broad, relatively stable shelves and platforms in coastal lagoons, in tidal flats, and on the surfaces of volcanic or carbonate rocks that stand within reach of light microbial mats spread across the substrate. A microbial mat is a dense, multi-layered sheet of microorganisms embedded in sticky substances that they secrete. These mats bind sediment grains, trap finer particles carried by currents, and form cohesive surfaces that can persist through many cycles of flooding, drying, and burial. In cross-section, a mature mat in these late Archean settings often shows distinct layers, each dominated by a different set of microbes, adapted to a particular combination of light redox state and nutrient availability. At the very top of many mats closest to the incoming light are microbes that carry out oxygen-producing photosynthesis. These organisms, commonly grouped under the label cyanobacteria, in the rock record use water as an electron donor, fix carbon dioxide into organic matter, and release molecular oxygen as a waste product. Beneath them, where light intensity is lower and its quality is altered by absorption in the upper layer, other phototrophic microbes use forms of photosynthesis that do not produce oxygen. Instead of drawing electrons from water, they draw them from reduced compounds such as hydrogen sulfide, ferrous iron, or organic molecules. Deeper still below the reach of useful light microbes that do not depend on photosynthesis, rely on chemical energy from the breakdown of organic matter and from redox reactions involving sulfur iron, carbon, hydrogen, and nitrogen. Together, these stacked communities create microscale chemical gradients that are far steeper than any that exist in the overlying water column or the open ocean. During the day when sunlight is strong, the upper layer of a mat fixes carbon and releases oxygen at a rate that can for a time outpace the immediate consumption of these products. Within a thin film of water overlying the mat, oxygen concentrations can rise to levels that are significant on the scale of microbial metabolism, even though the surrounding bulk water remains almost entirely anoxic. At the same time, organic matter produced near the surface begins to move downward, either by diffusion or by slow physical transport within the mat. As this organic matter is broken down by heterotrophic microbes in deeper layers, oxidants such as nitrate sulfate or ferric iron are reduced, and reduced products such as hydrogen sulfide, ferrous iron, methane, and carbon dioxide are generated. Some of these reduced products diffuse upward and meet residual oxygen or other oxidants in intermediate layers where further reactions occur. Over a typical day-night cycle, the strengths and positions of these microscale gradients shift as light intensity rises and falls, as temperatures change slightly, and as the physical environment is disturbed by waves, tides, or rain. In this way, each mat functions as a compact reactor in which dozens of coupled processes of photosynthesis, respiration, fermentation, oxidation, and reduction operate in parallel. The diversity of metabolisms in these mats is already high, In addition to oxygen-producing and anoxygenic phototrophs, there are microbes that oxidize reduced sulfur compounds when oxidants are available, microbes that reduce sulfate to sulfide when organic substrates are present, microbes that reduce ferric iron to ferrous iron, and microbes that produce methane from carbon dioxide and hydrogen, or from small organic molecules under strictly anoxic conditions. There are also microbes that consume methane when traces of oxygen or other suitable oxidants are present. Nitrogen fixers convert atmospheric nitrogen dissolved in water into reactive forms that can be incorporated into biomass, while other microbes transform ammonium into nitrate or reduce nitrate back to nitrogen gas, along pathways that depend sensitively on the local presence or absence of oxygen. This metabolic richness allows mats to use a wide range of chemical resources from the surrounding environment and to respond flexibly to changes in supply. On larger scales, mats occur not as isolated patches, but as extensive pavements that can coat entire tidal flats and shallow platforms. In some regions, wave and current action periodically breaks pieces off these pavements and transports them along with trapped sediment into slightly deeper settings where they are buried and preserved. Over long periods, repeated cycles of growth, burial and cementation of mats produce layered structures known as stromatolites. Stromatolites are preserved as laminated sedimentary rocks, often with domed columnar or branching shapes that reflect patterns of microbial growth and sediment trapping. They are common in many Archean and early Proterozoic successions and provide one of the best direct lines of evidence for the presence of extensive microbial mats at the time. The exact biological communities that build each stromatolite are not fully known because the original cells and soft material are usually destroyed or altered during burial and metamorphism, but the lamination shapes and associated minerals indicate sustained microbial influence on sedimentation and early diagenesis. Stromatolite-bearing successions from the late Archean document a world in which these mat-building communities are widespread in shallow marine environments, though their abundance and distribution can vary with basin setting and with broader environmental conditions. Not all mats form stromatolites, however. Some mats remain planar or only weakly undulating, especially on flat tidal flats or in sheltered lagoons. Others grow on steep surfaces such as the sides of volcanic blocks or carbonate mounds, where their main effect is to stabilize loose material and to alter the immediate chemical environment at the rock-water interface. Still others develop in subtidal settings where they never fully emerge into air, but remain submerged, responding mainly to variations in light and water movement, rather than to drying and flooding. In each case, the mat modifies the fluxes of elements between water and substrate, promoting some reactions and suppressing others. The cumulative impact of many mats acting over long times influences the chemistry of entire basins. As oxygen-producing mats fix carbon, and a fraction of that carbon is buried rather than remineralized, they contribute to a global tendency toward oxidation, because bury-reduced carbon is no longer available to consume oxygen. At the same time, the same mats can enhance the delivery and cycling of reduced sulfur and iron, because their deeper layers and underlying sediments are sites of intense sulfate reduction and iron reduction when suitable minerals and oxidants are available. The products of these reactions, especially hydrogen sulfide and ferrous iron, can move back into the overlying waters and participate in further cycles of oxidation and reduction. In this way, mats both generate oxygen and help maintain powerful local sinks, for it reinforcing the pattern seen at larger scales in the pre-event oceans. Microbial life in this stage is still entirely microscopic and simple in body plan, yet ecosystems are already ecologically complex. No animals, land plants, or large algae exist, and even the timing and extent of early eukaryotes remain uncertain, with current evidence suggesting that if they are present at all, they are rare or confined to particular environments. The biosphere is therefore dominated by bacteria and archaea, and by viruses that infect them. Genetic and metabolic diversity is high, even if morphological diversity is limited, and this diversity is expressed most strongly in the way microbes partition chemical niches in space and time. Some lineages favour strongly reducing conditions and are restricted to deeper layers and anoxic waters, while others tolerate or require small amounts of oxygen and are confined to surfaces and interfaces. Still others move actively within gradients seeking optimal combinations of light and chemicals. Outside the mats themselves, the surrounding sediments and pore waters host dispersed microbial communities that extend the reach of biogeochemical cycling into the upper crust. Pore spaces between grains, fractures in rocks, and microcavities within minerals provide sheltered habitats where fluids percolate slowly and where redox reactions proceed at modest but continuous rates. In coastal zones and shallow basins, these subsurface communities exchange chemical species with the overlying mats and waters participating in the same interconnected cycles of carbon, sulfur, nitrogen, and metals. Over distances of only a few centimeters, conditions can shift from mildly oxygen, influence near the surface to strongly reducing at depth, and different metabolic groups occupy these layers accordingly. The details of this microbial world are inferred rather than observed directly. Stromatolites, laminated sediments, geochemical signatures in carbon, sulfur, nitrogen, and iron isotopes, and the presence of certain organic molecules in ancient rocks all point to a biosphere rich in mats and metabolically diverse microbes. The precise identities, relationships, and distributions of these organisms remain subjects of ongoing research, and there is still debate about exactly when some metabolisms arise or become widespread. What is clear, however, is that by this late Archean stage, the living part of the Earth system already organizes itself into structured communities that profoundly influence the cycling of key elements. These communities operate mainly in the shallowest parts of the oceans and at interfaces within sediments and rocks, where they draw on light and chemical gradients to sustain themselves. As they grow, die, and are buried, they leave behind mineral assemblages and isotopic patterns that mark the gradual shift from an overwhelmingly reducing planet toward one that is internally rearranging its surface redox balance, even though free oxygen in the global atmosphere remains extremely low. During the interval known as the Great Oxidation Event, the outer envelope of the planet enters a new chemical regime in which free oxygen, once only a fleeting trace, becomes a persistent if still modest component of the atmosphere. The sun has grown slightly brighter than it was in the earliest Archean, but remains dimmer than in later ages, so the need for strong greenhouse warming continues. Yet the mixture of gases that performs this warming is changing. Nitrogen still provides most of the atmospheric bulk, and carbon dioxide continues to act as an important greenhouse gas, but the long-term balance between oxygen sources and sinks begins to shift in favour of oxygen. For hundreds of millions of years before this interval, oxygen-producing photosynthesis in the oceans supplies a continuous upward flux of molecular oxygen, while volcanic gases reduce species from the crust and mantle, and iron and sulfur in the oceans, and sediments act as powerful sinks that remove this oxygen almost as quickly as it is formed. Over time, the burial of reduced forms of carbon, sulfur, and iron in sediments gradually draws down the inventory of readily available sinks at the surface. As this inventory declines, the same biological oxygen flux that once barely maintained tiny local oases now starts to push against a weakened capacity for consumption. The Great Oxidation Event is the period when this imbalance becomes big enough that oxygen can accumulate in the atmosphere to levels that are small by modern standards, yet large compared with the almost negligible concentrations of earlier times. In the air above the oceans and continents, this change does not happen everywhere at once or in a sharp step. Instead, atmospheric oxygen appears to rise in a stepwise and possibly oscillatory fashion, with intervals of faster increase and periods of relative stability or even partial decline. Geological evidence suggests that oxygen first reaches a background level in the lower atmosphere that is high enough to alter photochemical reactions involving sulfur and carbon and to prevent some highly oxygen-sensitive minerals from surviving long at the surface. The absolute abundance of oxygen at this stage remains uncertain, and proposed values span a range of fractions of the present atmospheric level, but all estimates agree that the concentration is still far below what later animals and land plants require. In this new atmospheric regime, photochemistry reorganizes. Ultraviolet radiation from the sun continues to break apart molecules high in the atmosphere, but the presence of more molecular oxygen allows a thicker layer of ozone to form. Ozone is produced when oxygen molecules are split by high-energy photons, and the resulting oxygen atoms recombine with other oxygen molecules. Once a sufficient column of oxygen exists, this ozone layer becomes dense enough to absorb a large share of the most energetic ultraviolet radiation before it can reach lower levels. The result is a sharp change in the way sulfur-bearing gases and other compounds respond to sunlight. Before the event, the absence of a substantial ozone shield allows deep penetration of high-energy ultraviolet light, which drives reactions that impart distinctive so-called mass-independent patterns to sulfur isotopes in aerosols and sulfur-bearing minerals. During the Great Oxidation Interval, these mass-independent signatures disappear from sedimentary records, indicating that ozone and oxygen now intercept enough ultraviolet radiation high in the atmosphere to change the character of sulfur photochemistry. The loss of these signatures is one of the clearest markers of a new atmospheric state, even though it does not by itself fix the exact oxygen level. At the same time, the lifetime of methane in the atmosphere shortens as oxygen concentrations rise. Methane reacts with oxygen directly, and with oxidizing radicals whose abundance increases in an oxygen-rich and ozone-bearing air column. As a result, methane can no longer build up to the very high concentrations that may have existed in some earlier Archean intervals, and its contribution to greenhouse warming declines. Carbon dioxide continues to warm the planet, and other gases contribute, but the net greenhouse effect changes. Climate models and geological evidence suggest that episodes of cooling and even extensive glaciation may accompany this reduction in methane, though the precise timing and extent of such cooling, relative to the different stages of oxygen rise, are still under study. What is clear is that the composition of the outer atmosphere is now tied more strongly than before to the balance between biological production of oxygen and the burial of reduced materials, and less to the ability of methane and other reduced gases to accumulate unchecked. The appearance of a more oxidizing atmosphere also affects aerosol formation. In a strongly reducing Archean air, thick organic hazes can form when high methane levels and ultraviolet light drive complex carbon chemistry, producing particles that scatter and absorb sunlight. As methane levels drop and oxygen rises, these hazes become less stable or less extensive, and the sky above many regions may shift toward a clearer state with a more familiar blue hue, though regional variations remain likely. New types of aerosols emerge as sulfur dioxide and other sulfur gases are oxidized more efficiently to sulfate, which can nucleate tiny droplets or coat existing particles. These sulfate-containing aerosols influence cloud formation and radiative transfer, reflecting some incoming sunlight back to space and modifying the distribution of heating and cooling in the atmosphere. Lightning and high-altitude electrical processes now occur in a gas mixture with more oxygen, and ozone altering the rate at which nitrogen oxides form. These nitrogen oxides can act both as greenhouse gases and as reactive intermediates that affect ozone, methane, and other species, weaving additional feedbacks into the atmospheric chemistry. Near the surface, the partial pressure of oxygen climbs to values that begin to matter for weathering reactions on land and for gas exchange with surface waters. In soils and on rock surfaces, oxygen in air, and in thin water, films oxidizes ferrous iron to ferric iron, favours the formation of red and brown iron oxides, and changes the stability of a wide range of minerals. In earlier times, minerals such as pyrite and uraninite can be transported as loose grains in rivers and preserved as detrital particles in sediments because the environment is too reducing to oxidize them quickly. As oxygen levels rise during the Great Oxidation Event, these minerals become less stable in many surface settings, and their detrital preservation becomes rare or disappears. Instead, iron tends to oxidize and either remains in place as weathering products or is transported as soluble ferric complexes that later precipitate elsewhere. These shifts in mineral stability produce suites of rocks and soils that, when examined in younger outcrop, record the first widespread appearance of oxidized conditions at or near the land surface. The rates at which these weathering reactions proceed depend on climate, rock type and topography, and they can vary widely from one region to another, but the global trend is toward a surface environment in which oxygen becomes an important reactant rather than a negligible trace. Exchange of gases between air and ocean also responds to the new atmospheric composition. As the partial pressure of oxygen in the lower atmosphere rises, more oxygen dissolves into the surface ocean, where it is not immediately consumed by reactions with reduced species. In regions where surface waters are well mixed and sinks are relatively weak, this exchange can maintain small but persistent oxygenated layers that interact with underlying reduced waters. In regions where reduced species remain abundant, much of the incoming oxygen is still drawn down, yet the net flux from air to sea now has the potential to support oxygenated surface films over wider areas and to influence the depth of redox fronts. The details of these interactions fall mainly within the domain of ocean chemistry, but they are driven from above by the evolving state of the atmosphere. On longer timescales, the new oxidizing power of the air changes the global cycles of carbon, sulfur, nitrogen, and many metals. Oxidative weathering on land increases the flux of sulfate and other oxidized species to the oceans, while enhanced burial of oxidized forms of sulfur and iron in marine sediments removes oxidizing power from the surface system. Carbon buried as organic matter or as carbonate continues to regulate the balance between carbon dioxide and oxygen, and feedbacks between continental growth, erosion and sedimentation influence how efficiently reduced and oxidized materials are sequestered. The interplay of these processes helps set the trajectory of oxygen beyond the initial rise, yet the precise shape of that trajectory remains uncertain. Different proxies, each with their own limitations and time resolution, yield somewhat different pictures of how quickly oxygen increases and how it behaves after the main step. Some lines of evidence favour a relatively sharp rise to a new low plateau, followed by a long interval, with only modest further change. Others allow for more gradual or multi-stepped growth with possible temporary declines. The true path likely includes elements of both with regional and temporal variability superposed on a global trend. Despite these uncertainties, the broad picture is clear. During the Great Oxidation Event, the outermost layer of the Earth system moves from a state in which oxygen is present only in tiny unstable traces to a state in which oxygen becomes a permanent though still minor background gas. This reorganizes atmospheric photochemistry, alters greenhouse gas balances, and begins to reshape weathering and gas exchange at the surface. The skies over the Archean oceans and continental fragments are therefore no longer simply the hazy, strongly reducing skies of earlier times, but are now part of a more oxidizing environment that will in later intervals drive further changes in the oceans, the rocks and the biosphere that live beneath it, even though those later stages have not yet unfolded. During the core of the Great Oxidation Event, the oceans sit between an atmosphere that is becoming more oxidizing and a crust and mantle that still deliver large amounts of reduced material. The result is not a fully oxygenated ocean, but a set of basins in which redox contrasts sharpen. Vertical layering strengthens and chemical fronts migrate in response to changing fluxes from above and below. The surface ocean is now in more regular contact with air that holds a small but persistent background of oxygen. In regions where winds and currents mix the upper waters effectively, this contact allows the surface layer to gain and hold dissolved oxygen at concentrations that, while still low, compared with later ages are higher and more stable than in earlier Archean times. In areas with high biological productivity and limited resupply of reduced species from depth, this surface layer can extend tens of meters downward and persist through seasonal and climatic fluctuations. In other regions, especially where upwelling brings reduced deep water toward the surface, the oxygenated layer remains thin and fragile, collapsing when physical conditions favour the upward movement of reduced substances. Beneath the surface, stratification becomes a key control on ocean chemistry. Warm, relatively fresh water in the mixed layer overlies cooler, saltier, and more reduced water at depth. The transition between these layers marks a redox boundary, where dissolved oxygen from above meets reduced iron sulfur and organic matter from below. At this interface, ferrous iron oxidizes to ferric iron and precipitates as iron-rich minerals. Hydrogen sulfide is oxidized to sulfate or elemental sulfur, and organic matter is broken down by a combination of aerobic and anaerobic processes. The exact depth of this boundary and its sharpness vary from place to place, and through time depending on climate basin geometry and the balance between oxygen delivery and reduced species supply. In many basins, the classic banded iron formations that record large-scale iron cycling reach their peak development around this time. These rocks consist of repeated thin layers of iron-rich minerals and silica-rich material, and they are interpreted as the products of interactions between ferrous iron-rich waters and new oxygen. In deeper parts of some Archean and Paleoproterozoic basins, ferrous iron accumulates in anoxic waters that are separated from the surface by strong stratification. When conditions allow mixing or upwelling, or when oxygen penetrates downward along density surfaces, oxidation of this iron leads to the formation of solid iron oxides, or hydroxides that settle to the seafloor, often interlayered with chert. During the height of the Great Oxidation Interval, these processes appear to become more widespread or more efficient in some settings, leading to extensive iron-rich deposits. As oxygen continues to gain ground in the atmosphere and in surface waters, the character of iron cycling shifts. Oxidative weathering on land now delivers more ferric iron to rivers and coastal zones, and some of this iron precipitates close to shore, rather than remaining in reduced form and travelling into deeper basins. At the same time as more ferrous iron is removed from the water column and buried as oxidized minerals, the total inventory of dissolved ferrous iron in the oceans declines. In many reconstructions, this combination of changing sources and sinks contributes to a gradual reduction in the long-term formation of classic banded iron formations after their main heyday, although iron-rich sediments do not disappear entirely. The details of this transition depend on local tectonics, basin shape and climate, and remain the subject of active research. Manganese also responds strongly to the new redox structure of the oceans. Under very low oxygen conditions, manganese remains mainly in reduced soluble forms. As oxygen penetrates surface waters and redox boundaries, manganese can be oxidized to form solid manganese oxides that are highly reactive and can scavenge other trace metals from seawater. These oxides may form near the chemocline, the depth zone, where chemical gradients are steep, and then settle to greater depths where they can be reduced again if conditions become anoxic. During the Great Oxidation Interval, large manganese-rich sedimentary deposits appear in some regions, and these are often interpreted as markers of episodes when oxygenated waters expanded and interacted with manganese-rich deeper waters on a large scale. The sulfur cycle in the oceans is reshaped at the same time. Increased oxidative weathering of sulfide minerals on land raises the delivery of sulfate to the oceans through rivers. As a result, sulfate concentrations in seawater, which were likely low in much of the Archean, begin to rise, though estimates of exact values and their timing carry substantial uncertainties. Higher sulfate levels support more extensive microbial sulfate reduction in anoxic parts of the water column and in sediments. In zones where organic matter supply is high and oxygen is scarce or absent, microbes use sulfate as an electron acceptor, producing hydrogen sulfide that accumulates in pore waters and sometimes in deeper basin waters. Where this hydrogen sulfide reaches iron-rich layers, iron sulfide minerals such as pyrite form and are buried. In some restricted basins, especially where the supply of sulfate is high and circulation is limited, deep waters can become sulfidic over large volumes, a condition often called euxinic. In other basins, deep waters remain rich in ferrous iron and poor in sulfide, a state often termed ferruginous. Evidence from iron and sulfur isotopes from trace metal distributions and from sedimentary facies suggests that both ferruginous and euxinic conditions occur during and after the Great Oxidation Interval, with their relative importance varying among basins and through time. The carbon system in the ocean continues to tie biological productivity to redox balance. Oxygen-producing photosynthesis in surface waters fixes carbon dioxide into organic matter, some of which is recycled locally, while some sinks into deeper layers and sediments. Where oxygen is available, aerobic respiration converts organic matter back to carbon dioxide and water-consuming oxygen in the process. Where oxygen is absent but sulfate, nitrate or ferric iron are available, other forms of respiration proceed, producing hydrogen, sulfide, ammonium or ferrous iron. Where none of these oxidants are abundant, fermentation and methanogenesis dominate, leading to the production of methane and other reduced carbon species. Burial of a fraction of the organic matter without complete oxidation removes reduced carbon from active cycles and leaves an equivalent amount of oxygen behind in the surface system. Some intervals in the early Proterozoic carbon isotope record, including a prolonged positive excursion that begins near the end of the main oxygen rise, are often interpreted as signs of enhanced organic carbon burial on a global scale. The exact timing of this excursion relative to different phases of the Great Oxidation Event is still debated, but the general link between organic burial and oxygen accumulation is a central part of how the oceans influence the atmosphere in this time. Nutrient cycles adapt to the evolving redox landscape. Phosphorus remains a limiting nutrient for primary production in many settings, and its availability is controlled by the balance between riverine input recycling from sediments and burial in minerals and organic matter. Under more oxidizing conditions in surface waters and upper sediments, phosphorus can bind strongly to iron oxides, which may act as a trap that removes phosphorus from the water column and transports it to the seafloor. In more reducing environments, the dissolution of iron oxides can release phosphorus back into pore waters and overlying waters, promoting further productivity. Nitrogen cycles also feel the influence of oxygen. In oxygenated surface waters, ammonium produced by the breakdown of organic matter can be oxidized to nitrate, a process that requires oxygen and creates a form of nitrogen that can be used by many types of phytoplankton. At the margins of oxygen, minimum zones where oxygen becomes scarce but nitrate is present, microbes can convert nitrate back to nitrogen gas, a process that closes the loop and returns nitrogen to the atmosphere. The relative importance of nitrogen fixation, nitrification and denitrification in different basins depends on the detailed structure of oxygen profiles and on the distribution of organic matter degradation. These interactions between nutrients productivity and redox state help regulate the rate at which oxygen continues to be produced and stored. Physically, the oceans during the Great Oxidation Interval are shaped by the same broad forces that act in other eras: heat from the sun, and interior rotation of the planet, and the positions of continents and mid-ocean ridges. Winds drive surface currents, and upwelling moving oxygen-rich surface waters into new regions, and bringing reduced deep waters upward. Tides and storms stir coastal and shelf areas, intermittently deepening the mixed layer and altering the depth of redox boundaries. Over longer timescales, plate motions rearrange continents, and ocean basins changing the pathways of currents and the locations of upwelling and downwelling regions. These physical changes modulate the extent and persistence of oxygenated surface waters and the reach of reduced deep waters into shallower zones. From the perspective of the sedimentary record, the oceans at the height of the Great Oxidation Event leave behind a complex pattern of rocks that encode these physical and chemical changes. Thick successions of banded iron formations, manganese-rich layers, carbonates, black shales, and other sediments occur in many cratons, often interlayered in ways that suggest repeated shifts in redox conditions and in the sources and sinks of key elements. Some intervals show evidence for expanded oxygenated surface waters and widespread iron oxidation, while others record the dominance of anoxic and sulfidic conditions at depth. Isotope systems in carbon, sulfur, nitrogen, iron, and other elements provide overlapping but sometimes ambiguous views of these changes. Taken together, these lines of evidence point to an ocean that is neither uniformly oxygenated nor uniformly anoxic, but instead organized into a patchwork of redox states that evolve in step with the changing atmosphere and with the ongoing burial of reduced materials. In this stage, the oceans act as an intermediary layer that receives oxygen from the atmosphere and from photosynthetic production and transfers oxidizing power to the rocks and sediments that accumulate on their floors. They also continue to supply reduced species from the crust and mantle into the surface system. The balance between these opposing tendencies expressed through the redox structure of the water column and the nature of sediments controls how far and how fast oxygen can rise in the air above, while preserving in the geological record the clues that allow later observers to reconstruct the conditions that prevail during the Great Oxidation Event itself. In the oceans and on the limited land surfaces of the Great Oxidation Interval, microbial life continues to occupy almost every environment where liquid water and chemical energy are available, but the gradual rise of oxygen in air and surface waters alters the rules that govern which metabolisms thrive and where they can exist. The biosphere remains dominated by bacteria and archaea, with viruses as important agents of infection and genetic exchange, and there is still no evidence for complex plants or animals. Even so, the structure of microbial communities shifts as some lineages face new oxidative stresses. Others take advantage of more efficient energy pathways that depend on oxygen, and many retreat into refuges where conditions remain strongly reducing. From a broad view, the main changes appear first in the sunlit surface ocean and in shallow sediments. Here the interaction between oxygen-producing photosynthesis and the new oxidizing atmosphere above leads to surface waters that in many regions hold a small but persistent concentration of dissolved oxygen. Photosynthetic microbes that use water as an electron donor already play a central role in primary production. Before the event and during its main interval, they continue to dominate many parts of the photic zone. Their ability to tolerate and even benefit from higher local oxygen levels gives them an advantage over some purely anaerobic phototrophs, especially in well-mixed surface layers where reduced compounds are scarce. As a result, communities in the upper ocean shift toward assemblages in which oxygen-producing photosynthesis supplies most of the organic matter that supports food webs and biogeochemical cycles. At the same time, new or expanded groups of microbes appear that use oxygen directly in respiration. Aerobic respiration is the process by which organisms use oxygen to oxidize organic matter or reduced inorganic compounds releasing energy, carbon dioxide, and water. Because oxygen has a high oxidizing power, this pathway yields more energy per unit of substrate than most anaerobic alternatives. Microbes that can exploit even low oxygen concentrations are therefore able to grow and divide more quickly when suitable substrates are present. In surface waters, and in the upper parts of sediments that exchange gases with the ocean, these aerobic or microaerophilic organisms take up residence alongside older anaerobic groups. They consume oxygen as they oxidize organic matter, forming a new link between photosynthetic oxygen production and the breakdown of biomass. This link helps shape vertical profiles of both oxygen and organic carbon, and sets the stage for more complex redox cycling. Not all microbes benefit from the new oxidizing conditions. Many strictly anaerobic lineages are sensitive to oxygen, which can damage cellular components and interfere with their metabolic machinery. For these organisms, survival now depends more strongly than before on access to refuges where oxygen remains low. In the water column, such refuges persist in deeper layers below the oxygenated surface films, and within oxygen minimum zones where consumption of oxygen outpaces its supply. In sediments, refuge zones occur just a few millimeters or centimeters below the sediment-water interface, where oxygen delivered from above has been fully consumed by aerobic respiration and chemical reactions. Within these anoxic layers, sulfate reducers methanogens and other anaerobes continue to operate in much the same way as they do in the pre-event world, transforming organic matter and inorganic substrates into reduced products such as hydrogen, sulfide methane, and ferrous iron. The boundaries between oxygen-exposed and anoxic zones become sharper as atmospheric oxygen rises. In a typical shallow marine setting during this interval, the overlying water may contain some dissolved oxygen, especially during periods of strong mixing or high photosynthetic activity. At the sediment surface, this oxygen is consumed rapidly by microbes and abiotic reactions, so that concentrations fall steeply with depth. The uppermost sediment grains host thin biofilms and mats of microbes that can tolerate variable oxygen levels, while deeper layers host communities adapted to strictly anoxic conditions. Seasonal or episodic changes in bottom water oxygen can cause the boundary between these communities to migrate up and down, forcing microbes either to adjust or to be replaced by neighbours better suited to the new conditions. Similar patterns occur on the surfaces of rocks, stromatolites, and microbial pavements, where oxygen-rich microfilms overlay more reducing interior zones. In the open ocean, especially in regions where upwelling brings nutrient-rich water to the surface, oxygen dynamics interact closely with productivity. High nutrient supply supports dense blooms of photosynthetic microbes, which generate organic matter and oxygen near the surface. As some of this organic matter sinks, it fuels respiration in deeper waters where oxygen is used up. If the rate of oxygen resupply by circulation and mixing is too slow to match, this demand oxygen minimum zones intensify. Within these zones, microbes that use nitrate sulfate or other oxidants become more important. Denitrifiers convert nitrate to nitrogen gas, linking nitrogen cycling to redox state, while sulfate reducers generate hydrogen sulfide that can accumulate in deeper waters or react with metals. At the upper and lower boundaries of such zones, where small amounts of oxygen coexist with reduced substrates, microbes that can simultaneously access both types of resources find unique niches. Some bacteria, for example, may oxidize sulfide or methane with oxygen, under very low oxygen concentrations, helping to control the upward flux of these reduced gases. On the scale of individual microbial mats, the rise of oxygen changes internal organisation and external impact. Mats in tidal flats, lagoons and shallow shelves continue to grow as layered structures, but the upper layers now experience more consistent exposure to oxygenated water, and in some settings to air. This encourages the development of communities that can withstand oxidative stress during part of the day and then operate under lower oxygen at other times. Protective pigments, antioxidant enzymes and repair mechanisms help these microbes cope with reactive oxygen species generated by light and oxygen together. Deeper in the mats, anaerobic processes remain active, but the depth at which specific metabolic zones occur can shift compared with earlier times. For example, the layer where sulfate reduction peaks may move slightly downward as oxygen penetrates farther into the mat, while zones of methanogenesis may retreat even deeper or into adjacent sediments. The net result is that mats remain powerful drivers of local geochemistry, but the relative strengths of their internal processes adjust to the new balance between oxidants and reductants. Microbial communities associated with mineral surfaces also feel the changing environment. In soils and weathering profiles on land, oxygenated pore waters interact with minerals such as pyrite ferromagnesian silicates and organic rich horizons. Microbes that can catalyze or accelerate these oxidation reactions, sometimes drawing energy from them, become more common. Iron-oxidizing bacteria, for example, use ferrous iron as an electron donor and oxygen as an electron acceptor, forming ferric iron minerals as products. Sulfur-oxidizing bacteria play similar roles in converting reduced sulfur compounds to sulfate. These organisms help shape the chemistry of runoff and groundwater, increasing the flux of sulfate ferric iron and acidity into rivers and eventually the oceans. At the same time, microbes that mediate reduction reactions in deeper parts of weathering profiles and in subsurface aquifers continue to operate under oxygen-poor conditions, closing local redox loops. Diversity at the genetic and metabolic level continues to expand during this interval, although the details are difficult to reconstruct from the rock record alone. Molecular clock analyses based on comparisons of modern genomes suggest that many major groups of bacteria and archaea diversify around or before the time of the Great Oxidation Event, and that several key metabolic innovations may arise or spread in association with changing redox conditions. However, the exact timing of these events remains uncertain, and different methods and datasets yield somewhat different estimates. What can be said with confidence is that by the early Proterozoic, the microbial world already includes lineages capable of exploiting a wide range of redox couples, from oxygen and nitrate at the top of the gradient to carbon dioxide and hydrogen at the bottom. Whether early eukaryotes participate significantly in these ecosystems during the main oxygen rise is less clear. Some fossil-like microstructures and biomarker signals have been interpreted as possible evidence for early eukaryotic life in late Archean or earliest Proterozoic rocks, but these interpretations remain debated and alternative explanations exist. If eukaryotes are present, they likely form a minor component of microbial communities rather than dominant primary producers or consumers. The bulk of primary production and nutrient recycling still rests with prokaryotic microbes. Throughout the Great Oxidation Interval, feedbacks between microbial activity and environmental conditions continue to operate. As oxygen-tolerant and oxygen-using microbes spread, they can enhance the drawdown of reduced species, further weakening some sinks for oxygen. At the same time, vigorous aerobic respiration can consume large amounts of oxygen, where organic matter supply is high, limiting the spread of oxygen into deeper waters. Methanogens in anoxic sediments and deeper waters continue to produce methane, but methanotrophs in oxic or suboxic layers oxidize some of this methane before it can reach the atmosphere. In this way, microbial communities help modulate greenhouse gas levels and thus climate, even though they have no agency or purpose in doing so. The interplay of these processes leads to a biosphere that is spatially more structured with respect to oxygen than in earlier times. The near-surface environment now includes a patchwork of niches defined by different oxygen concentrations, from well-mixed surface waters with persistent oxygen to fluctuating transition zones to stable anoxic refuges in sediments, deep basins, and parts of the subsurface. Microbial lineages align themselves along this gradient according to their metabolic capacities and sensitivities. Over geological timescales, the differential success and survival of these lineages leave imprints in the distribution of isotopes in the types of minerals that form and in the organic molecules that are preserved in rocks. These imprints provide the main window into the shifting microbial world of the Great Oxidation Event. They show that the rise of oxygen is not simply a change in atmospheric composition, but a reorganization of the living surface layer of the planet, in which familiar types of microbial processes continue, but are rearranged and reweighted in response to a new, more oxidizing environment that still falls far short of later levels. In the early Proterozoic aftermath of the Great Oxidation Event, the climate and surface environments of the planet adjust to a new balance between a slightly brighter sun, an atmosphere that now holds a persistent background of oxygen, and a greenhouse effect that is changing as methane declines and carbon dioxide continues to evolve. The outer boundary of the Earth system is no longer the strongly reducing Archean sky, yet it is still far from the modern atmosphere. Nitrogen continues to supply most of the atmospheric mass. Carbon dioxide remains an important greenhouse gas, and its concentration reflects the ongoing competition between volcanic outgassing, silicate weathering on land, carbonate formation in the oceans, and burial of carbon in sediments. Methane, which once may have reached high abundances under very low oxygen, is now more effectively destroyed by reactions with oxygen and oxidizing radicals, so its contribution to warming decreases. The net result is a climate system that can experience large swings in temperature as greenhouse gas levels and planetary albedo change in response to tectonics, weathering, and evolving aerosols and clouds. Evidence from ancient rocks indicates that in the early Proterozoic, soon after the main rise of oxygen, the planet experiences several extended glacial episodes in which ice advances to low latitudes on land, and in some reconstructions sea ice may reach near tropical regions. The exact number, timing, and severity of these glaciations, often grouped under the name Huronian, remain the subject of active research, and it is not yet fully settled how closely they coincide with different stages of the Great Oxidation Interval. What is clear is that thick deposits of glacially influenced sediments such as diamictites and associated faces occur in sequences that also record changes in atmospheric redox state. These deposits show that the early Proterozoic climate is capable of sustaining cold intervals, in which large ice sheets grow on continents and persist for millions of years before retreating. Between and around these glacial episodes, warmer climates likely prevail with liquid water widespread and the hydrological cycle active. In cold intervals, ice sheets cover broad regions of high and middle latitude land, and even approach equatorial zones if some reconstructions are correct. These ice sheets carve valleys, erode bedrock, and deliver large amounts of rock flour and debris to surrounding oceans when they melt or calve. Sea level responds to the growth and decay of ice falling, as water is stored on land and rising again when ice melts. In warmer times between glacial episodes, rivers carve channels into previously glaciated surfaces, soils develop more fully, and vegetation is still absent on land, so bare rock, loose sediments, and microbial films constitute the main surface coverings. The day-to-day weather above these surfaces is guided by atmospheric circulation patterns that are broadly similar in structure to those that operate later with rising warm air near equatorial regions, sinking air in subtropics and storm tracks in mid-latitudes. But the detailed strength and position of these patterns depend on continent locations and on thermal contrasts that differ from those of later ages. Clouds and aerosols play central roles in mediating the early Proterozoic climate. The rise of oxygen and the associated development of an ozone layer alter the spectrum of ultraviolet radiation, reaching the lower atmosphere, changing the pathways by which sulfur and nitrogen species form aerosols. Sulfur dioxide released from volcanoes and from oxidative weathering of sulfide minerals is now more efficiently converted to sulfate, which contributes to fine particulate matter that can serve as cloud condensation nuclei. These sulfate-rich aerosols can brighten clouds by increasing the number of droplets, which enhances their ability to reflect sunlight back to space, and can also influence cloud lifetime and precipitation patterns. Organic compounds, produced by microbes and by photochemical reactions, add additional types of aerosol particles. The overall aerosol load in the early Proterozoic atmosphere likely fluctuates in response to volcanic activity, weathering rates, and biological productivity, leading to changes in planetary albedo on a range of timescales. On continental surfaces, weathering regimes respond directly to the new, oxidizing power of the air. In earlier Archean times, chemical weathering proceeds mostly under low oxygen conditions, favouring the breakdown of silicate minerals and the release of cations, while leaving many iron-bearing minerals in reduced forms. In the early Proterozoic, oxygen in air and in percolating waters accelerates the oxidation of ferrous iron. To ferric iron promotes the formation of iron oxides and hydroxides, and changes the suite of minerals that form in soils and regolith. This oxidative weathering produces more reddish and brownish weathering profiles, and alters the fluxes of iron, manganese, sulfur, and trace metals to rivers. It also strengthens the long-term negative feedback between climate and carbon dioxide as temperatures and rainfall increase. Chemical weathering rates rise, drawing down more carbon dioxide through silicate dissolution and carbonate formation, which in turn can cool the climate. When climates cool and weathering slows, volcanic outgassing can allow carbon dioxide to build up again. In the early Proterozoic, this feedback operates within a system that now includes oxygen-driven weathering reactions and a different mix of greenhouse gases than before, and its quantitative behaviour remains an area of uncertainty in climate models and geochemical reconstructions. On the limited land areas that rise above sea level surfaces are still largely barren of complex macroscopic life. There are no trees, grasses, or land animals, and even large microbial structures are restricted in extent. However, microbial communities do colonize some terrestrial and marginal settings. Thin biofilms and microbial crusts can form on moist rock surfaces in soil like layers, and along the margins of lakes, rivers, and coastal flats. These communities fix carbon cycle nutrients and influence mineral dissolution and precipitation at very small scales. Their presence may darken surfaces, slightly changing their reflectivity, and they can trap and bind sediment grains, influencing erosion and sediment transport. Yet they do not create the kind of thick organic rich soils or extensive vegetation cover that later moderates runoff and stabilizes landscapes. As a result, when intense rainfall occurs, rivers can carry large sediment loads from steep unprotected slopes, especially in regions recently deglaciated or uplifted by tectonic forces. The early Proterozoic hydrological cycle moves water between atmosphere, land, and ocean in familiar ways. Evaporation from the oceans and to a lesser extent lakes and moist soils supplies water vapour to the atmosphere. This vapour condenses into clouds when air masses cool, and precipitation falls as rain or snow depending on local temperature. In cold intervals, snowfall over ice sheets and highlands exceeds melting in some regions, adding to ice mass and sustaining glaciation. In warmer intervals, melting and rainfall feed rivers that return water to the oceans. The intensity and pattern of storms respond to temperature gradients between equator and poles, to seasonality set by the tilt of the planet's axis, and to the distribution of land and sea. During glacial episodes, strong thermal contrasts at the margins of ice sheets likely support vigorous storm tracks, while open oceans at lower latitudes supply moisture. In interglacial times, storm pathways adjust to changed temperature and surface conditions. Over millions of years, these processes round mountains fill basins with sediment and redistribute chemical elements between crust oceans and atmosphere. The surfaces of continental blocks in the early Proterozoic often show a patchwork of environments, glaciated uplands in some times, and places fluvial plains in others, coastal platforms where marine sediments accumulate, and interior basins that may host lakes or restricted seas. In each of these settings, the presence of oxygen in surface waters and pore fluids shifts mineral stability fields and reaction rates. For example, organic-rich muds deposited in lakes or in quiet marine embayments can experience more extensive aerobic degradation near their upper boundaries, while deeper parts of the same deposits become anoxic and host sulfate reduction and methanogenesis. Iron in these sediments may cycle between oxidized and reduced forms over short vertical distances, and the resulting mineral textures preserve a record of fluctuating redox conditions tied to climate and hydrology. The early Proterozoic surface system also engages in new couplings between the atmosphere and interior through the carbon and sulfur cycles. Oxidative weathering of pyrite and other sulfide minerals on land produces sulfate and acidity, which rivers carry to the oceans. Their sulfate participates in microbial and abiotic reactions that generate sulfide and various sulfur-bearing minerals, which when buried lock sulfur into the crust in oxidized or reduced forms. At the same time, weathering of carbonates and silicates along with burial of carbonate and organic carbon in sediments continues to adjust the partitioning of carbon between atmosphere, ocean, and rock. These coupled cycles influence atmospheric composition by controlling the long-term inventories of carbon dioxide and oxygen, and they interact with physical climate feedbacks driven by ice clouds and aerosols. The quantitative strengths and timescales of these couplings in the early Proterozoic are constrained only within broad ranges, and multiple scenarios remain consistent with available data. Some reconstructions, for example, suggest that periods of intense glaciation may coincide with low carbon dioxide levels, driven by strong weathering under an earlier, more methane-rich climate, while others emphasize the roles of changing volcanic degassing or continental growth. Despite these uncertainties, the broad picture is that the early Proterozoic climate system is sensitive to relatively modest changes in greenhouse gas concentrations and surface reflectivity, and that it toggles between cold and warmer states while remaining embedded in a world that is still significantly different from conditions that characterize much younger intervals of Earth history. Through all these shifts, the presence of a low but persistent background of atmospheric oxygen remains a defining feature. It underlies the formation of an ozone layer that moderates ultraviolet flux, at the surface shapes the chemistry of aerosols and rainwater, and drives new weathering pathways on land. It allows dissolved oxygen to persist in at least some surface waters, influencing nutrient cycles and sediment diagenesis. Yet oxygen levels are still well below modern values, and many environments at the surface and in the shallow subsurface remain anoxic, or only weakly oxygen influenced. The early Proterozoic surface. Earth, in the wake of the Great Oxidation Event, is a patchwork of climates and environments, in which ice, open water, barren rock, thin soils and microbial films coexist under skies that are more oxidizing than before, but still support a biosphere that is simple in structure compared with those of much later Earth history. In the early Proterozoic oceans that follow the main rise of atmospheric oxygen, the water masses adjust to a new but still intermediate state, in which oxygenated surface layers sit above deeper zones that remain largely anoxic, and the sediments on the seafloor record this arrangement in their minerals, textures, and chemical signatures. The atmosphere above supplies a low but persistent background of oxygen, and surface waters, in many basins, exchange gases with this air, often enough that they hold dissolved oxygen at levels that earlier Archean oceans do not sustain for long. In these upper layers, especially in regions with moderate to strong mixing by winds and currents, oxygen persists through day-night cycles and through seasonal changes and forms a relatively stable oxidizing cap. Below this cap, the water column is still strongly stratified by temperature, salinity, and density. Warm light surface water overlies cooler, saltier, and more stagnant deep water. At the boundary between them, gradients in chemical composition become pronounced. Dissolved oxygen diffuses downward and is carried by slow mixing, while reduced species such as ferrous iron, hydrogen, sulfide ammonium, and methane diffuse or are transported upward from deeper anoxic zones. At this redox boundary, oxygen and other oxidants meet reduced compounds, and a suite of reactions consumes both, forming new minerals and dissolved species that then move either upward or downward. The exact depth of this boundary varies among basins and through time, depending on climate, productivity, and circulation, but in many reconstructions it lies within the upper few hundred meters of the water column, keeping most of the deep ocean in a reduced state even as the air and surface waters become more oxidizing. A key feature of these aftermath oceans is the development of long-lived redox stratification on a global scale. Some basins have deep waters that are ferruginous, meaning they are rich in dissolved ferrous iron and poor in hydrogen sulfide. Others, especially more restricted or productive basins, host euxinic deep waters, which combine anoxia with significant concentrations of dissolved sulfide. The balance between ferruginous and euxinic conditions depends on the supply of iron and sulfate, the rate of organic matter degradation, and the physical isolation of basins. In ferruginous settings, hydrothermal vents, weathering inputs, and seafloor reactions supply ferrous iron that accumulates because oxygen rarely penetrates to the depths where it resides. In euxinic settings, higher sulfate levels and abundant organic matter allow microbial sulfate reduction to generate hydrogen sulfide that can fill deep basins and react with iron to form iron sulfide minerals. These contrasting states lead to different patterns of metal cycling and sediment composition, and they can coexist on the same planet in different regions at the same time. Sediments accumulating on the seafloor mirror this structured water column. On shallow shelves and platforms under oxygenated surface waters, sediments often include oxidized iron minerals, biogenic and abiogenic carbonates, and fine muds that contain organic matter, partly decomposed by aerobic processes. In deeper waters beneath the oxygenated cap, where the water is anoxic but still ferruginous, sediments may be rich in iron-bearing minerals that form when ferrous iron meets small amounts of oxygen or other oxidants near the redox boundary and then settle downward, or when iron reacts with phosphorus and other ions in pore waters. In euxinic basins, sediments frequently contain abundant iron sulfide minerals such as pyrite, along with organic rich muds whose preservation is enhanced by the absence of oxygen. The vertical stacking of these sediments over time produces stratigraphic sequences that record shifts in redox structure productivity and basin geometry, with transitions from more ferruginous to more sulfidic conditions or from more oxygenated to more anoxic states captured in changes in mineralogy and bulk composition. Nutrient cycles adapt to this new background. Phosphorus remains a central limiting nutrient for primary production, and its distribution is strongly affected by interactions between iron organic matter and redox state. In oxygenated surface waters and upper sediments, phosphorus tends to adsorb onto iron oxide minerals, and be removed from the water column as these minerals settle. When these particles cross into more reducing zones, iron oxides can dissolve, potentially releasing phosphorus back into pore waters and deeper layers. In ferruginous settings where iron is abundant but oxygen is scarce below the surface, this cycle can allow phosphorus to be recycled within the interior of the ocean, supporting productivity when some of it returns to the surface through upwelling. In euxinic settings, however, both iron and phosphorus may be trapped more efficiently in iron, sulfide and apatite-like minerals, leading to stronger long-term removal of phosphorus to sediments and a tighter coupling between redox state nutrient availability and productivity. The nitrogen cycle also responds to the new arrangement of oxygen and anoxia. In oxygenated surface layers, microbes oxidize ammonium to nitrate, a process that requires oxygen and creates a pool of oxidized nitrogen that many primary producers can use. At the edges and within oxygen minimum zones, microbes reduce nitrate back to nitrogen gas or to nitrous oxide under low oxygen conditions, returning nitrogen to the atmosphere and influencing the bioavailable nitrogen inventory. Deeper in the anoxic interior, ammonium can accumulate as organic matter degrades in the absence of oxygen and nitrate. Nitrogen-fixing microbes which convert atmospheric nitrogen, dissolved in seawater into reactive forms, continue to operate, especially in regions where fixed nitrogen is scarce. The balance between these processes controls how much reactive nitrogen is available to support productivity, and this balance depends on the vertical structure of oxygen and on the supply of organic matter. Over large areas, the early Proterozoic oceans likely host broad zones where nitrate is consumed, and ammonium and nitrogen gas dominate, while oxygen-rich surface patches maintain nitrification and support different community structures. Carbon cycles through these aftermath oceans along pathways already present but now weighted differently. Oxygen-producing photosynthesis in surface waters continues to fix carbon dioxide into organic matter, and some of this material is exported downward as sinking particles. In the oxygenated mixed layer, a portion of this organic matter is respired with oxygen, returning carbon dioxide to the water and consuming oxygen. Below the oxygenated cap in anoxic waters and sediments, anaerobic respiration and fermentation rely on sulfate, ferric, iron nitrate, and other oxidants where they are available, and on methanogenesis where they are not. Hydrogen sulfide and methane produced at depth can move upward where microbes in suboxic or oxic zones may oxidize them, linking deep anoxia to surface redox dynamics. A fraction of organic carbon escapes complete remineralization and is buried in sediments, especially in organic-rich muds of anoxic and euxinic settings. The burial of this reduced carbon represents a key long-term sink that allows oxygen to accumulate in the atmosphere and in surface waters. Carbonate carbon also records the operation of this system. In many early Proterozoic successions, carbon isotopes and carbonate rocks show prolonged intervals of positive values, often interpreted as signs of enhanced burial of organic carbon relative to carbonate. Such intervals suggest that on average more reduced carbon is being locked away in sediments than before, leaving behind a more oxidized surface reservoir. However, the exact magnitude, duration, and causes of these carbon isotope patterns remain under active investigation, and different hypotheses exist about their relation to oxygen levels, nutrient supply, and tectonic changes. The aftermath oceans also redistribute trace metals and other micronutrients important for microbial life. Elements such as molybdenum, copper, zinc, and nickel have solubilities and speciation that depend on redox state and on the presence of sulfide. In ferruginous waters, some of these trace metals may be relatively available, while in euxinic waters many bind strongly to sulfide and are removed into sediments. Because certain enzymes that support key metabolisms, including nitrogen fixation and some forms of photosynthesis and respiration, require these metals their distribution can influence which metabolic pathways are favoured in different parts of the ocean. Geochemical studies of trace metal concentrations in shales and other sediments from the early Proterozoic provide clues about how widespread anoxia and euxenia are, but they also reveal that metal availability is complex and that different basins experience different regimes. Physically, the circulation of these oceans continues to move water and dissolved components along long pathways. Surface currents driven by wind and planetary rotation transport oxygenated water and nutrients between basins, while deep currents driven by density differences and by inputs of heat and salt slowly exchange interior waters. Regions of upwelling bring nutrient-rich and often more reduced waters to the surface, fueling productivity and linking deep chemical reservoirs to the air and sunlight. In the early Proterozoic, the positions of continents and ridges, the shape of ocean basins and the strength of thermal gradients differ from those of later times, so the exact patterns of currents are not known and are reconstructed only in broad terms. Nonetheless, the coupling between physical circulation redox structure and nutrient distribution remains a central feature of the system. From the perspective of sedimentary rocks that form in this aftermath ocean, the seafloor becomes a canvas on which the interplay of oxygen, anoxia, nutrients and productivity paints patterns that later geologists read as evidence of this transition. Thick packages of black shales record intervals of high organic carbon burial under anoxic or euxinic conditions. Interbedded carbonates and mudstones capture shifts between more and less ventilated states. Iron formation deposition wanes in many regions, as the inventory of dissolved ferrous iron declines, and as more iron is trapped near coasts or in the upper ocean. Yet iron-rich layers still appear on smaller scales, marking local or episodic redox fronts. Sulfur isotope signatures in pyrite reflect a growing influence of microbial sulfate reduction as sulfate levels rise. Together, these records show that the early Proterozoic oceans do not revert to the strongly reducing Archean pattern, nor do they yet achieve the widely oxygenated state that characterizes much later times. Instead, they occupy an intermediate configuration in which an oxidizing atmosphere overlays oceans with long-lived redox stratification, in which sediments act as both sinks and sources for nutrients and redox active elements, and in which microbial communities continue to mediate almost every key transformation. In this state, the oceans play a dual role. They are recipients of the new oxidizing power delivered by the atmosphere and by surface photosynthesis, and at the same time they remain the main reservoirs for reduced species supplied from the interior and from organic matter degradation. The balance between these roles encoded in water column structure and sediment composition defines the early Proterozoic marine environment in the wake of the Great Oxidation Event, and sets the conditions under which the longer-term, more stabilized oxygen regime of the later Proterozoic will emerge. In the early Proterozoic oceans and on the modest areas of exposed land, microbial ecosystems continue to underpin all biological activity, but they now operate within a surface environment that holds a more stable background of oxygen at the top and long-lived anoxia below. The biosphere remains invisible at human scale, with no forests, animals or complex plants, and even large algal structures are uncertain or rare. Yet at microscopic scales, life is abundant and highly organized, and the new oxygen regime reshapes how microbial communities are distributed in space and how they exchange matter and energy with air, water and rock. In the open oceans, the sunlit surface layer supports widespread primary production by photosynthetic microbes. Cyanobacteria and related lineages that use water as an electron donor continue to dominate large parts of the photic zone, fixing carbon dioxide into organic matter and releasing molecular oxygen. These organisms are adapted to low nutrient conditions, variable light and low but persistent oxygen concentrations. Some occupy the very uppermost waters where light is strongest, and exchange with the atmosphere is direct. Others inhabit slightly deeper layers where light is weaker but more stable, and where competition for nutrients is different. Anoxygenic phototrophs that rely on reduced sulfur ion or organic compounds also persist, especially at depths where light still penetrates, but oxygen is scarce and reduced substrates diffuse upward from deeper water. The resulting vertical arrangement of phototrophs reflect both the quality and intensity of light and the shape of redox gradients in the upper ocean. Beneath the producers, heterotrophic microbes that consume organic matter fill much of the remaining space. In the oxygenated surface layer, aerobic heterotrophs gain an energetic advantage by using oxygen in respiration. They attach to particles, live freely in the water, and form biofilms on any available surface. As organic matter from the surface sinks, these organisms oxidize it back to carbon dioxide and water-consuming oxygen and generating heat and dissolved inorganic carbon. This respiration helps define the depth to which oxygen can persist, because where organic matter flux is high and circulation is modest, oxygen is used up more quickly. Below the depth where oxygen falls to very low levels, anaerobic microbes take over. These microbes use nitrate, sulfate, ferric iron and carbon dioxide as electron acceptors, producing nitrogen gas, hydrogen, sulfide, ferrous iron, methane and other reduced products. In many parts of the early Proterozoic ocean, this transition zone between oxic and anoxic conditions is sharp and stable over long timescales, creating a boundary that separates communities adapted to different redox states. The structure of oxygen minimum zones becomes more persistent than in earlier Archean oceans. In regions of strong upwelling and high productivity, surface waters gain nutrients from below, photosynthesis increases, and large amounts of organic matter sink into underlying layers. The respiration and anaerobic processes consume available oxygen, creating extended volumes of water that are suboxic or anoxic despite the presence of an oxygenated surface cap. Within these zones, microbes that perform denitrification, which converts nitrate to nitrogen gas, and microbes that carry out anaerobic oxidation of organic matter using sulfate or metal oxides, become key players in nutrient and redox cycling. Methanotrophs that oxidize methane at very low oxygen concentrations, or with nitrate as an oxidant, form thin but important layers at the interfaces where methane from deeper waters meets small amounts of oxidants from above. This layered arrangement allows different metabolic pathways to occupy distinct depths, yet they remain coupled through the movement of dissolved species and particles. On continental shelves and platforms, shallow marine ecosystems are shaped by both oxygenated waters overhead and the proximity of sediments, rocks, and land-derived inputs. Extensive microbial mats continue to form on tidal flats, subtidal banks, and the surfaces of carbonate and volcanic substrates. In many regions, stromatolites and related microbialites remain abundant, recording repeated cycles of mat growth, sediment trapping, and early mineral precipitation. In the early Proterozoic, some successions show a wide variety of stromatolite shapes, including domes, columns, and branching structures, implying that mat-building communities respond sensitively to water depth, wave energy, sediment load, and chemistry. The organisms within these mats experience a different oxygen regime from their Archean predecessors. Surface layers of mats are now in more regular contact with oxygenated water and sometimes with air during low tides or exposure events. Cyanobacteria and other oxygen-tolerant phototrophs inhabit these layers and can maintain positive oxygen levels for longer intervals during the day. Deeper layers still become anoxic as respiration and anaerobic processes proceed, but the depth at which specific metabolisms peak can shift. Sulfate reducers, which convert sulfate to hydrogen, Sulfide using organic substrates often operate immediately below the oxygen-exposed zone, while methanogens, which produce methane from carbon dioxide and hydrogen or from small organic compounds, retreat further into sediments or into restricted pores where oxidants rarely reach. Iron and sulfur oxidizing microbes flourish at microboundaries, where oxygen diffuses into ferrous iron-rich or sulfide-rich zones, catalyzing the transformation of these reduced minerals into oxidized forms and altering local pH and mineralogy. The combined activity of these communities in shallow settings influences how carbonate minerals precipitate, how trace metals are concentrated or removed, and how much organic matter becomes buried and preserved. The early Proterozoic seafloor beneath deeper waters also hosts complex microbial ecosystems. In sediments below oxygenated surface waters, a thin oxidized veneer overlies thicker anoxic layers. In the veneer, aerobic microbes oxidize reduced compounds arriving from below, while in the underlying anoxic sediments, sulfate reducers, iron, reducers, methanogens and fermenters break down organic matter and transform minerals. In ferruginous basins, microbes that reduce ferric iron to ferrous iron can use iron oxides delivered from the water column as electron acceptors, coupling iron cycling to carbon and sulfur cycles. In euxinic basins, microbes that reduce sulfate dominate deep sedimentary zones, and the hydrogen sulfide they produce reacts with iron to form pyrite. These processes generate distinctive chemical and isotopic gradients with depth that are later preserved in mineral assemblages and isotopic compositions. At some locations, hydrothermal vents and diffuse flow sites deliver hot, chemically rich fluids into the deep ocean, creating local ecosystems that draw energy from the oxidation of reduced compounds, such as hydrogen, hydrogen sulfide and ferrous iron, even when sunlight is absent. The presence or absence of oxygen in waters overlying these vents influences which metabolisms are most successful. Yet in many deep settings, oxygen levels remain low enough that chemolithotrophic communities can operate under largely anoxic conditions. The subsurface biosphere extends this microbial world into the upper crust. Pore waters in sediments, fractures in rocks, and microcavities in minerals house microbes that live at low energy fluxes and slow metabolic rates. These organisms draw on redox couples available in their surroundings, such as sulfate and methane ion oxides, and organic matter or hydrogen and carbon dioxide. They may have long generation times and exist at low cell densities, yet their total biomass over the vast volumes of subsurface habitat can be significant. Evidence for such a deep biosphere in the early Proterozoic is indirect, and comes from isotopic patterns, mineral textures and analogies with the modern deep biosphere, but it's consistent with an Earth whose surface and shallow interior are permeated by microbial activity to considerable depths wherever water can circulate. On land, the early Proterozoic microbial world is more limited in extent but still important for surface processes. Exposed rock surfaces, thin soils and ephemeral pools host microbial films and crusts wherever moisture persists for enough time. These communities include photosynthetic microbes that form thin green or brown layers on rock, and heterotrophic microbes and fungi-like organisms that break down organic matter and interact with minerals. Some microbes live inside rocks as endolithic communities occupying tiny pore spaces and cracks, where they are shielded from extremes of temperature and ultraviolet radiation, while still receiving some light and water. In weathering profiles, microbes accelerate the breakdown of minerals by producing acids, chelating compounds and redox reactions that dissolve or transform mineral phases. Through these actions, they influence the release of nutrients such as phosphorus and trace metals to rivers and eventually to the oceans. Viral and genetic interactions overlay all of these ecosystems. Viruses infect bacteria and archaea in surface waters, sediments, and the subsurface lysing cells, and releasing organic matter and nutrients into surrounding environments. This viral shunt recycles carbon and other elements within microbial communities and affects which lineages flourish or decline. Horizontal gene transfer, the movement of genetic material between organisms outside standard parent-to-offspring inheritance, allows metabolic traits to spread across different groups of microbes, potentially facilitating adaptation to new redox conditions or nutrient regimes. These processes leave no direct fossil record, but modern patterns of microbial genomes indicate that they have long been important in microbial evolution and ecology. The presence and influence of eukaryote cells with internal compartments such as nuclei in these early Proterozoic ecosystems remain less clear. Some microfossils and organic molecules have been interpreted as signs of early eukaryotic life in rocks from this broad time interval, suggesting that eukaryotic microbes may already be present in at least some environments. Other studies question these interpretations or place the major expansion of eukaryotes later. If eukaryotes are present during the early Proterozoic aftermath of the Great Oxidation Event, they likely occupy restricted niches and contribute modestly to total biomass compared with bacteria and archaea. Their ecological roles at this stage are uncertain, and current data do not yet support a detailed reconstruction of their distribution. Across all these settings, the key feature of early Proterozoic microbial ecosystems is their organization around long-lived oxygen gradients. The atmosphere and surface ocean provide a persistent, albeit low oxygen reservoir that supports aerobic metabolisms and stabilizes oxidized mineral phases. At the same time, large volumes of water, sediment and rock remain anoxic or only weakly oxygen influenced, sustaining a wide range of anaerobic metabolisms. Microbial lineages partition these environments according to their tolerances and metabolic capacities, giving rise to a biosphere that is chemically diverse and spatially structured, even though it lacks visible complexity. Over geological timescales in this new regime, the patterns established by these ecosystems feed back into the global cycles of carbon, sulfur, nitrogen, and metals, and they imprint the rock record with the signatures that identify the early Proterozoic as a distinct state of the Earth system shaped by, and in turn shaping the presence of sustained but still modest oxygen in the surface environment. After the main rise of atmospheric oxygen and the more immediate early Proterozoic adjustments, the planet enters a long interval in which the outer environment settles into a comparatively stable but still intermediate state. The air above the surface is no longer the strongly reducing atmosphere of the Archean, yet it is still far from the oxygen-rich mixture that surrounds the world in much later times. Nitrogen continues to make up most of the atmospheric mass. Oxygen now holds a permanent place as a background gas rather than a fleeting trace, but its abundance remains modest. Multiple lines of geochemical evidence, including signals from iron, sulfur, chromium, and other redox-sensitive elements, point to oxygen levels that are higher than in the Archean and early Great Oxidation phases, yet still well below those of later eras. Estimates place these levels within a range that may amount to at most a few tenths of the modern atmospheric fraction, and possibly less, and the exact value and its variations through this long span remain uncertain. What matters for the Earth system is that oxygen is sufficiently abundant and stable to maintain an extensive ozone layer to sustain oxidative weathering on land, and to keep at least some surface waters persistently oxygenated, while large volumes of the ocean interior and the subsurface remain anoxic. This new balance defines the character of Proterozoic air and light. In the upper atmosphere, the presence of molecular oxygen supports a column of ozone that absorbs much of the high-energy ultraviolet radiation arriving from the sun. Compared with the Great Oxidation interval itself, this ozone layer is now more continuous and long-lived, tied to a relatively steady oxygen column. Ultraviolet photons at the most damaging wavelengths are largely intercepted high above the surface, while less energetic wavelengths penetrate deeper into the atmosphere. This shielding reduces the rate at which some photochemical reactions occur in the lower air and at the surface, altering the formation of radicals, oxidants and aerosols. It also decreases the direct ultraviolet stress on surface waters, rocks and microbial communities, although the exact intensity of ultraviolet light at ground level and its variation with latitude and altitude remain only broadly constrained. The vertical structure of the atmosphere reflects this radiative balance. In the stratosphere, where ozone absorbs ultraviolet radiation and re-emits energy as heat, a temperature inversion develops with temperatures increasing upward over a certain range. Below this, in the troposphere, temperatures decrease with height, and convection clouds and weather systems dominate. The precise altitude and strength of the temperature inversion depend on ozone abundance, greenhouse gas concentrations, and the intensity of solar radiation, which itself is slowly increasing as the star ages. Over this long Proterozoic interval, the sun brightens by a modest fraction compared with earlier times, raising the incoming solar energy, but the climate response is moderated by changes in atmospheric composition and by feedbacks involving clouds, ice, and weathering. Greenhouse gases in this stabilized atmosphere differ from those of the Archean. Methane, once able to accumulate to high levels in a strongly reducing air, now has a shorter lifetime, because reactions with oxygen, ozone, and reactive radicals destroy it more efficiently. As a result, methane concentrations are generally lower and contribute less to greenhouse warming than before the Great Oxidation Event, although they can still vary with biological activity and volcanic input. Carbon dioxide remains a major greenhouse gas, and its concentration is set by long-term exchanges between the mantle crust oceans and atmosphere. Volcanic degassing delivers carbon dioxide to the air, whereas silicate weathering, carbonate formation and burial of carbon in sediments remove it. Climate models and geochemical reconstruction suggest that carbon dioxide levels in this Proterozoic interval are likely higher than in much later times, yet lower than peak Archean values, but quantitative estimates carry significant uncertainty. Water vapor, which responds rapidly to temperature, continues to act as a powerful amplifier of climate variations. Trace gases such as nitrous oxide and carbon monoxide participate in photochemistry and radiation, but their mean abundances and roles in this ancient atmosphere are less well constrained. Aerosols form an important intermediate component between radiation and climate. Sulfate aerosols arise from the oxidation of sulfur dioxide emitted by volcanoes, and from the oxidative weathering of sulfide minerals on land processes that are both facilitated by the presence of oxygen. Organic aerosols form from volatile compounds produced by microbial communities and from photochemical reactions in the atmosphere. Dust particles are lofted from continental surfaces wherever arid conditions and sparse surface cover allow winds to erode fine material. Sea salt aerosols are generated by waves and spray over the oceans. The mix of these particles controls how much sunlight is scattered back to space, how much is absorbed in the air, and how easily clouds form. In the stabilized Proterozoic atmosphere, sulfate and dust are likely significant contributors, especially downwind of tectonically active regions and glaciated terrains, though the exact distribution and loading are not known in detail. Together, aerosols and clouds set the planetary albedo and modulate the surface energy balance. The large-scale circulation of the atmosphere follows patterns controlled by rotation heating and the distribution of land and sea. Warm air rises most strongly near low latitudes where solar input is highest. As it ascends and moves poleward, it cools and eventually sinks at subtropical belts, giving rise to overturning cells that drive trade winds and subtropical high-pressure zones. At higher latitudes, temperature contrasts between equator and poles support jet streams and storm tracks. The positions and strengths of these features depend on the arrangement of continents, the presence or absence of large ice sheets in the mean climate state. During warmer intervals with limited ice temperature gradients may be weaker altering storm paths and precipitation patterns. During colder phases with expanded ice, especially near the poles, gradients intensify and circulation becomes more vigorous in some belts. The Proterozoic configuration of continents and oceans differs from any later arrangement, so the details of airflow are unique to this time, yet the same physical principles apply. These circulation patterns, together with aerosols and greenhouse gases, determine how light and heat are distributed over the surface. At low latitudes, sunlight is more direct and intense, producing warmer conditions and stronger convection. At high latitudes, sunlight arrives at a lower angle and is spread over a larger area, producing cooler conditions, and where ice or snow is present, a higher reflectivity that sends more light back to space. Seasonal shifts in the tilt of the planet's axis modulate these contrasts, bringing warmer summers and colder winters at mid and high latitudes. Overland day-night cycles and seasonal changes in insolation drive variations in temperature and humidity that shape weather patterns and the hydrological cycle. Over the oceans, the thermal inertia of water smooths some of these fluctuations, providing a more stable boundary for the air. From the perspective of light at the surface, the skies of this stabilized Proterozoic world are clearer on average than those of a strongly hazy Archean, yet they are still punctuated by clouds and aerosols. When aerosol loadings are moderate and skies are relatively clean, direct sunlight dominates, and the brightness of the sun at midday is high, though still lower than in much later times because the star itself emits slightly less energy. When aerosols and clouds are abundant, the proportion of diffuse light increases and the surface receives more scattered radiation and less direct beam. In coastal regions and downwind of dusty or volcanic areas, the colour and clarity of the sky can vary as particle concentrations change. The presence of an ozone layer also influences the spectrum of light, reducing the shortest wavelength ultraviolet component and leaving a visible and near ultraviolet band that is transmitted more efficiently. In aquatic environments, this light field sets the depth and quality of the photic zone. In clear open ocean waters, blue and green wavelengths penetrate tens of meters, sometimes more, allowing photosynthetic organisms to inhabit a relatively thick upper layer. In more turbid coastal or shelf waters, where sediments dissolved, organic matter and plankton are abundant, light is absorbed and scattered more strongly, and the photic zone becomes shallower. Because the spectrum of light changes with depth, with shorter wavelengths penetrating farther than longer ones, different pigments and photosystems have different advantages at different depths. The Proterozoic air and light regime therefore not only controls surface temperatures, but also shapes the vertical structure of photosynthetic niches in the oceans and in shallow waters on continental margins. Over continental surfaces, light interacts with bare rocks, thin soils, water bodies, and microbial films rather than dense vegetation. Exposed rocks reflect and absorb light according to their mineralogy and texture. Thin soils and regoliths formed under oxidative weathering can be darker than fresh rock and may lower albedo slightly in some regions. Microbial communities that occupy moist surfaces and shallow waters add patches of green-brown or other colours, but their total coverage is modest compared with later plant-dominated landscapes. Where snow and ice cover land or sea, especially at higher latitudes or during cooler intervals, reflectivity increases and more incoming solar energy is returned to space, reinforcing local cooling. Feedbacks between snow and ice, cover albedo and temperature continue to operate as they do in other eras, contributing to the stability or instability of climate states. From a geochemical perspective, the stabilized Proterozoic atmosphere and its light regime maintain a set of long-term feedbacks between radiation climate and the surface reservoirs of carbon and other elements. As the sun brightens slowly, silicate weathering at the surface driven by temperature rainfall, and the presence of carbon dioxide and oxygen in air and water adjust the drawdown of carbon dioxide, helping to keep surface temperatures within ranges that allow liquid water to persist over large areas. When climates tend toward warmer conditions, weathering intensifies and removes more carbon dioxide, which in turn reduces greenhouse warming. When climates cool, weathering slows, volcanic degassing becomes relatively more important, and carbon dioxide can accumulate. The presence of oxygen by enabling new weathering reactions influences the efficiency and character of these feedbacks. Aerosols and clouds modulate the effective solar input, adding another layer of response between the slowly brightening sun and the climate at the surface. All of these processes unfold over tens and hundreds of millions of years, giving the Proterozoic atmosphere a slowly evolving but relatively stable character, compared with the more rapid changes during the Great Oxidation Event itself. Within this framework, the air and light of the later Proterozoic provide a consistent outer setting for the ocean's rocks and microbial ecosystems below. Oxygen is sufficiently abundant to sustain an ozone shield drive widespread oxidative weathering and support oxygenated surface waters in many regions, yet it is still limited enough that anoxic and weakly oxygen-influenced environments remain common in the oceans and the subsurface. The distribution of sunlight both at the surface and within the upper ocean is controlled by this atmospheric structure and by the positions of continents and oceans. Together, these factors define the outermost layer of the Earth system in the stabilized Proterozoic state, within which the longer-term redox mosaics of the oceans and the persistent microenvironments of the biosphere develop and persist. Over the long span that follows the initial adjustments to the Great Oxidation Event, the oceans settle into a persistent pattern in which oxygenated surface layers, oxygen-poor interiors, and variable sulfidic zones coexist in a patchwork that covers the globe. The atmosphere above maintains a low but stable background of oxygen, and this oxygen diffuses into upper waters wherever contact between air and sea is regular and sinks, for oxygen are not overwhelming. In many open ocean regions, wind-driven mixing and surface currents keep the upper Thames to perhaps a few hundreds of meters in contact with the atmosphere, allowing dissolved oxygen to persist there through seasonal cycles. Below these layers, density stratification remains strong, and deeper waters stay isolated from the surface for long intervals. In such interior reservoirs, the absence of direct exchange with the atmosphere and the continuous input of reduced species from sinking organic matter and from the crust maintain anoxic conditions. The global ocean under these circumstances is neither uniformly oxygenated nor uniformly anoxic. Instead, it is organized in depth and across basins into distinct redox states that endure for tens of millions of years at a time, shifting only as continents move climate changes and the balance of inputs and outputs of oxidants and reductants evolves. In many basins, the dominant deep water state over these long intervals is ferruginous. In these waters, dissolved ferrous iron accumulates because hydrothermal vents, seafloor reactions and weathering deliver iron in reduced form, and because oxygen rarely penetrates to the depths where this iron resides. Organic matter that sinks into these ferruginous interiors is broken down by microbial communities that use sulfate ferric iron or other oxidants where they are available, and that turn to fermentation and methanogenesis where they are not. Hydrogen sulfide produced by sulfate reduction may form locally in sediments and in parts of the water column, but in strictly ferruginous basins it does not build up to the point of filling the entire deep water mass. In other basins, especially along some continental margins or in more restricted interior seaways, sulfate delivery from land and high organic matter flux create conditions in which hydrogen sulfide can accumulate in deeper layers. These basins become persistently euxinic with anoxic and sulfidic waters sitting below oxygenated or suboxic surface layers. Here, hydrogen sulfide reacts with iron to form iron sulfide minerals, and the resulting removal of iron from the water column feeds back on the cycling of phosphorus and trace metals. Between these two end members, there are many intermediate cases in which deep waters vary in time between ferruginous and euxinic, or in which euxinia is confined to certain depth ranges, slopes or basins connected by sills to more open waters. Currents, tides, and eddies constantly rearrange boundaries between these zones, but the overall pattern of redox heterogeneity persists over long spans. Within this framework, nutrient distributions and biogeochemical cycles develop characteristic Proterozoic behaviors. Phosphorus, the key limiting nutrient in many marine settings, is strongly influenced by interactions with iron and sulfide. In ferruginous basins, iron oxides that form near redox boundaries or in oxygenated surface waters can bind phosphorus and transport it downward. When these particles reach anoxic iron-rich layers, they may dissolve, releasing phosphorus back into the water column and allowing it to be returned to the surface by upwelling. This recycling supports primary production without requiring a large net loss of phosphorus to sediments. In euxinic basins, by contrast, phosphorus can be trapped more effectively. As iron combines with sulfide to form iron sulfide minerals, the capacity of iron oxides to bind phosphorus is reduced, and phosphorus may instead be buried as part of organic matter or as calcium phosphate minerals in sediments. This burial removes phosphorus from the active cycle and can over time limit productivity in the overlying waters. On a global scale, the balance between ferruginous and euxinic conditions affects how much phosphorus remains available to the biosphere and how efficiently organic carbon is produced and buried. Nitrogen cycles respond in parallel. Oxygenated surface waters support nitrification, in which ammonium is oxidized to nitrate, while oxygen-poor and anoxic zones host denitrification and related processes that convert nitrate back to nitrogen gas. In regions where suboxic or anoxic mid-depth waters are extensive, a large portion of the fixed nitrogen can be lost to the atmosphere, and nitrogen fixation by specialized microbes becomes essential to maintain the supply of bioavailable nitrogen. The relative importance of these processes varies among basins and through time, but the structure of the Proterozoic oceans ensures that nitrogen cycling remains closely tied to redox structure. Trace metals important for enzymes and metabolic pathways also follow patterns set by this redox mosaic. Elements such as molybdenum, uranium, vanadium, and copper are more soluble under oxidizing conditions and tend to be enriched in oxygenated and ferruginous waters, but they can be scavenged efficiently in sulfidic environments and removed to sediments. In euxinic basins, strong binding of many of these metals to sulfide and organic matter leads to shales and mudstones that are enriched in certain trace metals, compared with similar rocks from ferruginous or fully oxygenated settings. In ferruginous interiors, iron itself dominates redox buffering, and metals associated with iron cycling may be relatively more available. These differences in trace metal availability feed back on microbial metabolisms that require specific cofactors. For example, nitrogen-fixing enzymes that use molybdenum iron or vanadium draw on the ambient supply of these metals, and their efficiency and distribution can depend on how readily these elements are delivered to surface waters, because different basins experience different redox states. The global biosphere operates in a chemically heterogeneous world, in which some regions offer rich supplies of certain metals, while others are more limited. Geochemical measurements of trace metal abundances in Proterozoic sedimentary rocks capture this heterogeneity and provide one of the main lines of evidence for the persistent redox mosaics of these oceans. The physical circulation of the Proterozoic oceans helps maintain and rearrange this chemical patchwork. Surface currents driven by wind and influenced by the positions of continents and ridges transport oxygenated nutrient-bearing waters across basins. Where these currents diverge, upwelling brings deep reduced waters toward the surface, supplying nutrients that fuel primary production, but also delivering ferrous iron hydrogen sulfide and other reduced species that can consume oxygen. Where currents converge and waters sink, newly formed deep water spreads into the interior and slowly modifies existing reservoirs. In regions where cold, dense surface waters can form, such as high-latitude seas in cooler climates, these waters may carry oxygen deeper than usual, temporarily expanding oxygenated zones and shrinking anoxic interiors. In warmer periods, or in enclosed basins with limited ventilation, stratification strengthens and anoxia can expand upward. Over millions of years, the slow drift of continents changes the size and shape of basins, the locations of sills and gateways, and the pathways of major currents. These changes adjust the balance between well-ventilated and poorly ventilated regions, and can move ferruginous or euxinic domains from one part of the world to another without altering the underlying physics of stratification and exchange. On the seafloor, sediments integrate these physical and chemical patterns over time. In open ocean settings under oxygenated surface waters and ferruginous depths, fine-grained muds accumulate carrying organic matter iron, rich particles and trace metals that record the state of the overlying water column. In euxinic basins, black shales with high organic carbon and abundant iron sulfide minerals form, preserving both the intensity of anoxia and the efficiency of organic matter preservation. Carbonate platforms on shelves and slopes grow in waters that are at least intermittently oxygenated, and their compositions and isotopic signatures reflect the balance between local productivity, global carbon cycling, and redox structure offshore. Intervals of enhanced organic carbon burial leave their mark as positive excursions in carbonate-carbon isotopes, while variations in sulfur isotopes trace the extent and type of microbial sulfate reduction and sulfide burial. Iron and nitrogen isotopes add further constraints on the prevalence of ferruginous versus euxinic conditions and on the structure of the nitrogen cycle. Taken together, these sedimentary signals show that the redox mosaics of the Proterozoic oceans are not fleeting features but long-lived components of the Earth system that persist and reconfigure over much of this eon. Moving inward from whole basins to smaller scales, the same redox structure appears in miniature within water columns, boundary layers and pore spaces. At the centimetre to metre scale near redox boundaries, sharp gradients in oxygen, iron, sulfur and methane define narrow zones where microbes carry out particularly intense metabolisms. For instance, where small amounts of oxygen or nitrate meet sulfide diffusing upward from anoxic waters, or sediments sulfide oxidizing microbes form dense but thin layers that can turn hydrogen sulfide into sulfate and elemental sulfur. Where methane from deeper sediments encounters oxygen or sulfate, microbes perform aerobic or anaerobic methane oxidation, converting methane to carbon dioxide or bicarbonate and producing carbonate minerals. Within a few centimetres of sediment depth, oxygen can fall from measurable levels at the surface to undetectable levels below, while sulfide or ammonium rise in the opposite direction, creating stacked niches for different physiological groups. Mineral surfaces within these gradients provide sites where metals precipitate, dissolve or change valence state, and where biofilms influence the rates and products of these reactions. Over time, the accumulation of minerals such as pyrite, siderite, and various carbonate phases in these zones builds microstratigraphy that parallels the larger scale patterns seen at basin level. In this long-lived Proterozoic state, The oceans thus act as a layered, spatially variable medium in which oxygen, nutrients, metals, and reduced species are distributed in complex but enduring patterns. Large-scale redox mosaics sustained by the interplay of atmospheric composition, internal heat flow tectonics, and biological activity coexist with fine-scale chemical gradients that structure microbial habitats at the scale of grains and pores. The early biosphere that occupies these oceans and sediments experiences a world in which oxidizing and reducing environments lie close together in space, but differ greatly in chemistry, and it continues to arrange its metabolisms and communities along these gradients, while the overall oxygen level of the atmosphere remains modest and relatively stable over extended intervals of Proterozoic time. Within the stabilized Proterozoic state that follows the Great Oxidation Event and its early aftermath, the smallest environments at the surface of the planet carry the imprint of the new oxygen regime as clearly as entire basins and continents do. At scales of grains, pores, and thin films of water, oxygen-reduced compounds, nutrients and minerals meet in tight layered arrangements that support dense microbial activity. These microenvironments are the places where the transformed atmosphere and oceans interact most intimately with rock and living matter, and they provide the fine-scale structure that underlies the broader patterns of the early Proterozoic biosphere. In coastal zones and shallow marine settings, microbial mats continue to blanket sediments, rocks, and carbonate surfaces, but their internal chemical architecture reflects the presence of a more stable, oxygenated surface layer above. At the very top of a mat in direct contact with overlying water concentrations of dissolved oxygen can remain positive for much of the day, and sometimes through parts of the night if exchange with the atmosphere and photosynthetic production are strong enough. This thin oxygen-exposed layer hosts cyanobacteria and other phototrophs that tolerate oxygen, along with aerobic heterotrophs that consume freshly produced organic matter. Just below, over depths of millimeters to a few centimeters, oxygen levels drop sharply as it is used by microbial respiration and by reactions with reduced minerals. In this transition zone, microbes that can switch between aerobic and anaerobic metabolisms, or that can use low levels of oxygen alongside other oxidants, find niches. Deeper still, where oxygen effectively vanishes, hydrogen sulfide, ferrous, iron, methane, and ammonium become more abundant, and sulfate reducers, iron, reducers, fermenters, and methanogens dominate. The exact thickness and position of each layer vary with local conditions, including light intensity, sedimentation rate, tidal exposure, and the chemistry of overlying waters, but the overall structure remains that of a steep vertical sequence of redox zones compressed into a small physical space. Similar patterns appear in the boundary layer between oxygenated surface waters and anoxic interiors of the ocean. At the depth where oxygen is nearly exhausted and reduced species from below first become abundant narrow horizons form, in which redox reactions are especially intense. In these horizons, sulfide oxidizing microbes convert hydrogen sulfide to sulfate or elemental sulfur iron. Oxidizers transform ferrous iron to ferric iron, and microbes that carry out anaerobic oxidation of methane couple methane consumption to sulfate reduction. Mineral particles in these layers acquire coatings of iron oxides, manganese oxides, or sulfur, bearing faces that reflect the conditions under which they form. Even when the bulk water above and below is relatively uniform over tens of meters, the centimeters around these interfaces contain a diversity of chemical states and microbial communities. In sediments beneath both shallow and deep waters, pore spaces between grains host their own microscale gradients. At the sediment-water interface, a thin film of oxygenated water overlies grains whose uppermost surfaces may be coated with oxidized minerals. Within the top few millimeters, oxygen diffuses into pore waters and is consumed while organic matter arriving from the water column or produced in place is decomposed. The depth at which oxygen disappears depends on the rate of organic matter supply, the porosity and permeability of the sediment, and the concentration of oxygen in overlying waters. Immediately below this depth, nitrate, ferric ion, and sulfate act as electron acceptors for microbial respiration. Microbes that reduce nitrate to nitrogen gas, that reduce ferric ion to ferrous ion, and that reduce sulfate to sulfide occupy overlapping zones, each drawing energy from different combinations of substrates. The products of these reactions diffuse upward and downward, creating further gradients. At greater depths, in the same sediment column, where oxidants are scarce, and organic matter is more refractory. Methanogenesis and slow fermentation dominate, producing methane and small molecules that may move upward into zones where other microbes can consume them. Along this vertical path, mineral assemblages change with oxidized iron phases near the surface, giving way to iron sulfides carbonates or iron silicates at depth, and with carbon preserved in varying proportions between organic and inorganic forms. Fractures and pores in the upper crust extend these microenvironments away from the seafloor and deep into rocks. Groundwater or pore fluids flowing through these spaces carry dissolved oxygen only where they have recently contacted the surface or oxygenated waters. As they move along fractures, the oxygen they contain is consumed by reactions with ferrous iron in minerals, with reduced sulfur, and with organic matter in the rock. Within short distances, fluids can shift from mildly oxidizing to strongly reducing, and microbial communities track these shifts. Near points of recharge where oxygenated water enters aerobic and microaerophilic microbes colonize fracture walls and mineral surfaces, forming thin films that draw energy from the oxidation of reduced species in the rock. Farther along flow paths where oxygen has been consumed, sulfate reducers, methanogens, iron reducers, and other anaerobes inhabit microniches, sustained by slow fluxes of hydrogen carbon dioxide and other substrates generated by water-rock interactions and by the breakdown of any organic material. The rates of these processes are low compared with those at the surface, yet they proceed continuously over long times, allowing subsurface communities to persist and to participate in the long-term cycling of elements between deep and shallow reservoirs. On the limited land areas exposed above sea level, microenvironments in soils and weathering profiles similarly show the combined influence of oxygen from the air and reduced material from the crust. Thin soils formed under Proterozoic conditions contain mixtures of primary minerals, secondary clays, iron oxides, and organic matter produced by microbial and algal communities. Water films that coat grains and fill small pores during wet periods carry dissolved oxygen, carbon dioxide, and ions. At grain surfaces, microbes facilitate redox reactions and mineral dissolution by producing acids, chelating agents, and reactive metabolites. Ferrous iron in minerals near the surface oxidizes to ferric iron, forming coatings and cements that change the color and physical properties of the material. Sulfide minerals where present oxidize to sulfate and iron oxides, contributing acidity and dissolved salts to pore waters. In deeper parts of weathering profiles where oxygen penetration is limited and water exchange with the surface is slower, reduced phases may persist or form anew, and anaerobic microbes can inhabit protected niches. These small-scale processes collectively set the compositions of runoff and groundwater that flow into streams, rivers, lakes, and ultimately the oceans. Lakes, ephemeral ponds, and small basins on continents add further microenvironments to this Proterozoic surface. In these bodies of water, stratification, mixing, and redox gradients often mirror those in the oceans, but on shorter spatial and temporal scales. Shallow margins in contact with the atmosphere can be oxygenated, especially where photosynthetic microbes inhabit the water and the benthic surface. Deeper central parts may be anoxic and even sulfidic if organic matter supply is high and mixing is limited. Microbial communities arrange themselves accordingly, with oxygen-tolerant phototrophs and heterotrophs near the surface and anaerobic metabolisms below. Sediments at the bottom of such basins record the alternation between oxidizing and reducing conditions, sometimes on seasonal or decadal timescales, through laminae that differ in mineralogy and organic content. Over many cycles of filling, stratifying and draining these lakes and ponds contribute small but steady amounts of weathered material, dissolved solutes, and organic carbon to the broader surface system. Across all these settings, the microenvironments that define the inner layer of the early Proterozoic Earth system are deeply shaped by the presence of a persistent but modest background of oxygen. Oxygen reaches them not as a uniform bath, but as a gradient from the outside in. It diffuses from the atmosphere into oceans and soils, from surface waters into sediments, and from recharge zones into the subsurface. At each step it is opposed by reduced species coming from the interior and from organic matter degradation, and the points where these opposing fluxes meet are where the most active microscale processes occur. The Great Oxidation Event, along with the subsequent adjustments of the early Proterozoic, changes the strength and reach of these oxygen fluxes and alters the inventories of reduced compounds available to consume oxygen. As a result, many microenvironments that once experienced only transient or negligible oxygen now experience low stable levels, while others remain fully anoxic but are connected indirectly to oxidized reservoirs through diffusion and advection of dissolved species. The biosphere uses the full spectrum of these conditions, with microbial lineages occupying positions along each gradient that match their metabolic capacities. Some organisms specialize in the new oxygen, exposed niches exploiting aerobic respiration and oxygen-dependent biosynthetic pathways. Others remain restricted to anoxic cores of matte sediments and rocks. Still others position themselves at interfaces where both oxidants and reductants are available cycling elements between states and linking local reactions to global budgets. The physical and chemical changes associated with the Great Oxidation Event thus propagate all the way down to the smallest habitable spaces at the surface of the planet, rearranging the microscale structure of interactions between rock, water, air, and life. In this stabilized Proterozoic state, the Earth's early biosphere continues to exist on a world that is still far from modern conditions, yet is now durably transformed by the presence of sustained oxygen, expressed across a hierarchy of scales from atmospheric photochemistry down to films of fluid on mineral grains and thin layers in microbial mats,